Good morning, everyone. A very warm and enthusiastic welcome to all the distinguished guests, respected faculty members, and our esteemed participants. My name is Monith.
And my name is Shwetank, and it is our privilege to welcome you to Nano Jatha 2026, a celebration of innovation, knowledge, and the limitless possibilities of nanoscience and technology. So, to begin the event, we are going to show a glimpse of IIT Hyderabad via specially made video for this event, followed by a video of Nano Jatha. Followed by an event of Nano Jatha. It's a journey of Nano Jatha. This is the fourth time, and yeah, here it begins.
Year 2008, the vision that began in a modest campus, inventing and innovating in technology for humanity. Today, it has grown into a powerful institute of India's progress. Indian Institute of Technology, Hyderabad. In just 18 years, IIT Hyderabad has carved a distinct identity in education, research, and innovation among the fastest growing institutions in the country today. In national rankings and on global rankings, IIT Hyderabad continues to make a strong and steady mark. What began in an ordnance factory with just 111 students has now evolved into a thriving campus spread across 600 acres, shaping the future of over 5,700 students, setting new benchmarks in research, publications, and patents. IIT Hyderabad nurtures innovation from the very first semester through programs like Build and Broughty, encouraging students to become builders, not just learners. By hosting India's first inter-IIT undergraduate innovation meet, it has given young innovators a platform to grow and flourish. This is not just an institution, it is a laboratory of innovation and talent. Within its technology research park and innovation ecosystem, over 280 startups have emerged, creating more than 1,100 jobs and generating over 1,500 crore rupees in revenue. Here, the technologies of the future are taking shape today. From 6G communication to autonomous navigation, from artificial intelligence to 3D printing and cutting-edge deep tech research, IIT Hyderabad continues to lead at the frontiers of innovation. India's first 3D printed bridge, DigiBeam, bringing precise digital addressing to every doorstep, or even autonomous vehicles navigating roads and skies. These innovations are shaping IIT Hyderabad's global identity. In collaboration with the Japan International Cooperation Agency, a new chapter of education, innovation, and research is being written between India and Japan. At recent Japan Academic Day, 76 representatives of Japanese institutions gathered at IIT Hyderabad to strengthen global partnerships. IIT Hyderabad is more than a campus, it is a living, sustainable, and inspiring ecosystem, a home to thousands of trees, generating half of the energy from over 10,000 solar panels, and steadily moving towards a net zero vision by 2030. Through its rural development initiatives and student-led efforts, the Institute is also contributing to the growth of nearby rural communities. Life here goes beyond academics. Here, students think, create, play, and shape their dreams into reality. At the recently hosted Inter-IIT Sports Meet, thousands of participants from across the country experienced not just world-class sports facilities, but also the vibrant and inclusive spirit of IIT Hyderabad. From a humble beginning to a global identity, the journey of IIT Hyderabad is not just about 18 years, it is the story of building a global institution, moving forward with a vision of inventing and innovating in technology for humanity. Year 2000.
A big idea makes you discover yourself to be a greater person than you ever dreamt yourself to be, said Maharishi Patanjali in the Yoga Sutra around 500 BC. So, what is that big idea that is expected to change the way we live in the 21st century? Just imagine the next generation across the country drinking zero-contaminated, purest water. Milk staying fresh for days, ensuring adequate milk supply in every nook and corner of the country. Food for all becomes a reality. Humanity is living fearlessly as cancer cells get killed in totality. The country gets 100% additional highways within 10 years. Soldiers get wetsuit-like gear that is 100% bulletproof. Come to think of it, to make this dream a reality, research started in India thousands of years ago. India was a Suvarna Bhumi then. Come to think of it, Suvarna Bhasma, Loha Bhasma, Tamra Bhasma, Abharak, Shilajit in Ayurveda. The kajal that romanced with the beautiful eyes of Meena Kumari, Madhubala and Saira Banu, which hypnotized many a generations. All romance apart, even the terrific and gruesome Damascus blades wielded by Muslim fighters in the 17th century against Christian knights in Europe were forged from small cakes of steel known as words produced in ancient India. All these were the results of high-minded efforts in search of a big idea. What was that big idea? That big idea of ancient India, now rediscovered by the 21st century world, is called nanotechnology. And here we are today in Bangalore, the R&D hub of India, where nanotechnology is discussed in the same breath as cricket or sandalwood. Who made this happen? Who forged this quest for nanoscience? One man whose lifetime mission has been to pursue science. One man who at the age of 80 has the unfading curiosity like an 8-year-old child. The man who has published around 1,600 scientific papers and 49 books and is on the editorial boards of more than 20 leading professional journals and fellowship of major science academies. A man who is recognized across the world. The living legend who has been conferred with India's highest civilian award, Bharat Ratna. Chintamani Nagesa Ramachandra Rao. Under the visionary leadership of Professor C.N.R. Rao, the first edition of Bangalore Nano was launched in 2007, and it soon became the foremost event for nanoscience and industry in the country and a place where the world could connect with India. Bangalore India Nano will bring together the nanotech fraternity from across the globe, explore nano horizons with tutorials to educate and enlighten. B2B exhibition to do business. Research Industry Collaboration Hub. Awards to recognize the best in nanoscience and technology. And Nano for the Young program to nurture future talents.
In today's world, science and technology keep changing the way we live and the way we do things every day. one of the most important contributions of scientists in the last few years to science as well as to improving the quality of life has been nanoscience and technology. This area has already changed the way we administer medical aid in cancer, the way we perform reactions in industry, the way we use and generate new ways of producing materials of the smallest dimensions and use them for applications. These dimensions we talk about are very, very, very small. A nanometer is 10 to the power of minus 9 meter, extremely small. It is this science and technology that has aroused the interest of young and old and all over the world. And we in India have one major meeting to celebrate and also expose nanoscience and technology to the common man as well as to educators in Bangalore.
Nanotechnology is the new and emerging field of technology that deals with dimensions less than 100 nanometers. And if you put that in perspective, 100,000 nanometers fit into the thickness of a piece of paper. When Physics Nobel Prize winner Richard P. Feynman was at a dinner with his peers in 1959, he challenged them to write the entire 24 volumes of the Encyclopedia Britannica on the head of a pin. He wondered that if our cells could produce at such a small level, why couldn't we produce at a similar or even atomic level? He was sure guessing the future, and in time, computers that took up whole rooms occupied our pockets. This led to the coinage of the term nanotechnology in 1974 by a Tokyo Science University professor, Norio Taniguchi. In 1981, two IBM Zurich Research Laboratory employees, Gerd Binning and Heinrich Rohr, earned the Nobel Prize in Physics for inventing the scanning tunneling microscope. This microscope allowed for imaging at the atomic level in a vacuum, along with air, water, and other materials, withstanding temperatures from 0 to over 370 Kelvin. This would eventually lead to some pretty cool things. In 1989, IBM spelled the three letters in their logo, I, B, and M, using only 35 atoms of xenon, a nickel plate, and the scanning tunneling microscope. IBM used to be the biggest player in the computer industry, and now their stock share has decreased quite a lot since their peak. They also published a cute little movie in 2013 on the atom and the boy. Enjoy!
That was a fascinating video. It beautifully captured the essence of excellence of IIT Hyderabad and the transformative role of nanoscience and nanotechnology in addressing some of society's most pressing challenges. So, to mark the auspicious commencement of Nano Jatha 2026, we shall now begin with the traditional ceremonial lighting of lamp, symbolizing the triumph of knowledge over ignorance.
So, for that, may I respectfully invite our esteemed dignitaries, Professor B.L.V. Prasad, Director of Science, Professor B.S. Murthy, Director IIT Hyderabad, Professor Narhari Shastri, Dean SRC, Professor C. Mallareddy, Dean ITS, to kindly come forward and grace the occasion by lighting the ceremonial lamp.
शुभं कुरुत्वं कल्याणम् आरोग्यं धनसम्पदः शुभं कुरुत्वं कल्याणम् आरोग्यं धनसम्पदः शत्रुबुद्धिविनाशाय दीपज्योतिर्नमोऽस्तु ते दीपज्योतिर्नमोऽस्तु ते दीपज्योतिर्परब्रह्म दीपज्योतिर्जनार्दनः दीपज्योतिर्परब्रह्म दीपज्योतिर्जनार्दनः दीपो हरतु मे पापम् सन्ध्यादीपनमोऽस्तु ते ओ दीपब्रह्मरूपस्त्वम् ज्योतिषां प्रभुरव्ययः ओ दीपब्रह्मरूपस्त्वम् ज्योतिषां प्रभुरव्ययः आरोग्यं देहि पुत्रांश्च पतिं स्वच्छामि मे सदा रवेरस्तं समारभ्य यावत् सूर्योदयः.
May we now request our distinguished guests to kindly take their seats on the dais as we proceed with the inaugural session. So, please.
So now, calling out Dr. Suman to give bouquets to all the dignitaries as we announce their names. Professor B.S. Murthy, sir.
So, as we know, every successful event is the result of dedication, teamwork, and visionary leadership. As we begin today's program, we would like to invite our esteemed Nano Jatha coordinator, IIT Hyderabad, Dr. Narendra Kura, to join us on the stage to kindly welcome our distinguished dignitaries and to share some glimpse on the Nano Jatha. Please welcome. So.
Thank you. Good morning, everyone. A warm welcome to Nano Jatha, which is Professor C.N.R. Rao, to kind of ignite young minds with the power of hands-on demonstrations and popular lectures. We also extend our heartfelt gratitude to our Honorable Director, Professor B.S. Murthy sir. He is always there to uplift IIT Hyderabad. In fact, keep IIT Hyderabad at the front runner, like in terms of societal impact, by organizing the flagship events like this Nano Jatha. I also would like to thank our National Nano Jatha Coordinator, Professor B.L.V. Prasad sir, who kind of give us opportunity to host this event at IIT Hyderabad. Thank you very much, sir. And also I'm thankful to our Dean SRC, Professor Narasastri sir, and also Dean Innovation, Professor Mallareddy sir, for their support and encouragement all the time. So here, today we gathered to witness the celebration of science, especially nanoscience and technology. I'm sure it is going to be enriching experience to all of you. Just enjoy the celebration and then have fun. Yeah, thank you.
Thank you for your kind remarks, sir. So, Nano Jatha has evolved into an important platform that brings frontier research closer to the society. So, to take us through this inspiring journey, I invite Professor BLV Prasad, Chief Scientist at NCL Pune, and also the National Coordinator of Nano Jatha, to address the audience. Join me in welcoming Professor BLV Prasad on the stage with a big round of applause.
Good morning, Professor B.S. Murthy, Professor Narhar Shastri, Professor Mallareddy, and all the friends who have come from different parts of Hyderabad to join this Nano Jatha program. I thank Professor Narendra Kurra, and he actually said the right thing at the end, have fun. I think one of the things that we are missing in science, doing science, is having fun. I think science somehow is perceived as a bit of boring subject that you need to memorize a lot of things, that you need to write a lot of things, etc. But I think through these lectures and the demonstrations especially, what we want to display is that science is fun. And I also want to thank, I unfortunately do not see many of them here, probably they are still doing the work, all the volunteers from IIT Hyderabad who have come forward on a Sunday. I know it's not a very easy thing to do. So on a Sunday to join this program and then conduct this event, my sincere thanks to all of you. Some of you who are here, through you, I convey my thanks to all of you, all of the volunteers. And also, I also want to thank two of my CNS students, Mr. Naidu and Ms. Alia. Can you please raise your hands at least? Yeah. So these two people have been, this is a very interesting experience. If you don't mind, I want to share the experimental demonstrations, as you can see on the slide. They were developed by different institutions, including many ICERs, IITs, and CENS, JNC, etc. These are all packed into a big trunk, a suitcase. And this suitcase has to be carried everywhere we want to do. Of course, we have 6 such suitcases. These have to be carried, and unfortunately, these have to be carried by surface only, which means that they cannot be carried in a flight. Though we have money, we cannot put them in a flight because there are chemicals, etc. inside. So nobody would allow that. So these kids take these suitcases all over the India, including remote places like Nagaland, Shillong, Tirunelveli, Trivandrum, wherever we want. They take. They somehow one of the set of, yeah, exactly, not just these two, there are several of them, about, yeah, so all the volunteers, there are 6 kids that are traveling right now across India, right, like, so 6 suitcases are traveling, and many a times these suitcases are transferred from one place to the other, or like transferred from one team to the other on railway platforms. So one person gets down and it is picked up by other person. So it is a very interesting experience. It has been evolved because we have to do these events more or less in a very short span of time. So it's a very interesting experience. We have been enjoying it, doing, and I hope you will also enjoy, both the about the both talks and as well as the more important, the demonstrations in the afternoon. And once again, I thank Professor Murthy. I know him reasonably well for a very long time, a very long association in different kinds, including that we both studied in the same school, though we did not overlap in that school. And he has his passion for outreach is really contagious, basically. So it rubs on others. So I thank you, sir, for having us here. And again, providing all the opportunities. I hope some of you know that yesterday this place was bustling with activity, with lot of graduates, because the convocation was going on. Despite that, he said, let us do it, because this is very important. So thank you very much for that, Professor Murthy Garu, and all the other IIT Hyderabad colleagues who have really come forward and then provided us this Even I know providing a guest house in during this time would be very difficult, but despite that, providing us all the hospitality, etc., I sincerely thank you all. And one or two things about the event itself, and I will conclude. The event has two talks in the morning, one by Professor Murthy and followed by my talk, and followed by a quiz. And the quiz program, what we do is basically written quiz, and we don't want teams from the same college. You understand? I hope you understand what I am saying, right? We will force you to make teams across colleges, okay? Because this is an opportunity to make networking, and generally we are a bit hesitant to make networks. So we will force you to make teams across different colleges. The volunteers will do that. Please help them. Don't say that I don't want to join that team, this team, etc. Right? And there is a very hefty, I would say, reasonably good sum for the prizes. That also, thank you, Professor Murthy Garu, for doing that. So there is a good amount of money to be won. But don't worry about the money, etc. The more important is to have fun, right? That is very extremely important. And the talks themselves are not going to be a lot of throwing information at you, but the talks are generally curated so that they motivate you. And if you want to pursue science as a career, absolutely fine. That's a great fulfillment for the events. Even otherwise, I think we need to have a scientific temperament that is built in our daily life itself. Wherever we are, whatever we are doing, whether we are a bank employee or whatever it is, we need to have a scientific temperament. And if we have that right scientific temperament, then all these things whether we throw a bottle on the road or a chocolate wrapper on the road, these things also can be stopped once we have the right scientific temperament. I think that is extremely important, that we build that scientific temperament in our in our thought process. So with that, once again, thanks for coming all the way from different parts of the city to attend this program. And I repeat what Professor Kurra said: have fun. Thank you.
Thank you, sir, for sharing such beautiful remarks about Nano Jatha. You beautifully highlighted the importance of Nano Jatha event, which is happening today. So, it is now our distinct privilege to invite Professor B.S. Murthy, Director IIT Hyderabad, a distinguished academician and an eminent researcher whose contributions to material science and nanotechnologies have been widely recognized. And, sir, please, may we request you to come on the stage.
Namaste, brothers and sisters. Thank you very much for coming. As Prasad Garu pointed out, our relation goes to 2025 years back, when I first met him in Tokyo. Very interestingly, I spent about 2 years in a place called Tsukuba in Japan for 2 years, and actually I'm going to talk about that a little later. And I learned a technique of looking at things at a very small scale. I'm going to talk about that. But then I came to know that we both studied in the same school, in the same city. That has been another feather on the cap. But more importantly, about the gentleman in whose name this whole Nano Jatha is being celebrated. I have joined IIC Bangalore in 86 when he was the director. Amazing director. More importantly, that was the time, 87, 88 kind of time, was the thing where superconductors have been very hot topic. Every day. And Professor C.N.R. Rao is very well known in this particular field of superconductors. He's a structural chemist, as many of you possibly know. Every day we used to talk during dinner, during lunch, what is the temperature today? Okay, not the temperature in the city or in the IIC campus, but the temperature at which the newly kind of discovered superconductors have their TC. At what temperature? You all know superconductors have a particular specific temperature where below which they behave as superconductors, above which they don't behave, which is called a critical temperature. So every day people used to talk, today's temperature is this, today's TC is this, tomorrow's. I mean, that has been so a wonderful time that we went through. Amazing personality. And I attended his 90th birthday, which happened about a year back or so. And he could not speak on that day. His throat has become bad in recent years. But his own students spoke, saying that between his 75th year and 90th year, that 15 days, he has added about 500 papers. Okay, my whole life so far has been about 550 papers or so. In 15 years, he has added. And if you know, I think by now he has more than 2000 papers. Okay, so that is the personality whom we are celebrating today through this Nano Jatha. I think one big hand to such an inspiring personality. We all used to be so respectful to him, and that I mean, we always feel that he has missed, Nobel Prize. Hopefully, we still will see a day that would happen in his lifetime, and an amazing personality, Bharat Ratna. And many a times I see when I ask people about him, people know Sachin Tendulkar's Bharat Ratna, but they don't know about his Bharat Ratna. Both of them got the Bharat Ratna same year, for your information. So that's the kind of value that we give to science in India, unfortunately. But I hope all of you, at least today, sitting here, would really thoroughly enjoy. As Prasad pointed out, is all about experimenting. Enjoying. I am a strong believer. I am an experimentalist all through my life. We have done so many experiments, even at IIT Hyderabad for that matter, variety of experiments. But one experiment I am extremely happy about that I want to share is the experiment that we did last year. Many a times, some of you are possibly doing engineering. How many of you are doing engineering right now? Can you raise your hands? Okay. Reasonable number. So if you look at, as people say, all roads lead to Rome. Okay, every engineering, at the end of 4 years, you all stand in the queue for a TCS or a Google or a Infosys to get into some of those jobs. That's the current trend, I would say. So, but then, and India is known to be a country which is known to be a service country. And whenever I hear this word, actually it pains me a lot. Okay, in my view, India should be a technology country. It should be a product country. In fact, 2 weeks from now, I am going to be in Melbourne. If I go to a shop in Melbourne, I should be able to buy a product where it is written "Made in India." That's the day when we can say we are proud of being Indians, and India has become developed country. Okay, we are always, when I was born, I was told that we are a developing country, and I'm 62 now, so still we have been told that we are a developing country. But when that developed country comes into picture, our honorable Prime Minister keeps on talking about what is called Viksit Bharat. Almost every day you hear this term, Viksit Bharat by 2047. And if Viksit Bharat has to happen, you need to experiment. You need to learn to make products. And this is an experiment that we did last year. 600 BTech students joined us. I connected these 600 BTech students to about 100 faculty members, people like Narendra and a number of such exciting faculty we have who are all very passionate about their research. And we told these faculty that I'm giving you 6 students, 6 coming from 6 different branches. There is an interdisciplinarity there. And your job is just to have a cup of tea with them almost every week or more frequently than that, and ask them what do they want to build with their own hands. And I said, I will give you money for that. Okay, let them build something with their own hands. I wanted to see our hostels getting converted into workshops where you sit after dinner and build something. Okay, and this really has transformed many of them, because my intention was quite a number of students. I am a metallurgist, for your information, not a chemist or not a computer science fellow. Okay, and irrespective of your branch, students typically who join an IIT start learning from the first semester some coding, okay, some soft skills, and prepare themselves into that journey which I mentioned a few minutes back. And I wanted to see if some of them get transformed in the first semester itself, that they start making products. And once it happens, it's like, as Prasad mentioned, it's like a joy, it's a romance. Okay, and you get lost in it. Okay, many a times you would have felt, possibly when you are even in schools, when your teacher tells, let's make this product or something for a science exhibition or something like that, you possibly would not have even slept that night. Okay, when you do something which you like, okay, you put your whole heart in it. And now I told them first semester is very crucial. If we have lost them in the first semester, you have lost them forever. Okay, I said let us do this in first semester. Now we have students who have made 8-bit computers, 16-bit computers. They have made 3D printed microscopes, okay, levitation setups, variety of them. And for your information, next week we have the new batch of BTech students coming. We are going to put a big exhibition of all that products that these first semester students of last year have developed to tell these people. And only thing that I told all of them is whatever you make should be functional. It should show me something. It should show some result. If you are developing a 16-bit computer, it should do computation. Okay, and people are getting ready themselves to demonstrate this, so that we make this as an annual habit, that every first semester student, and once you start enjoying that, I would like to see somebody at the end of second year BTech saying that, sir, I have learned enough, let me take a break now. I want to start my startup. At IIT Hyderabad, we allow a student at the end of second year BTech, if you don't have any backlogs, that you take a break, we give you a diploma, and sit in the hostel with that certificate and stop studying and start your startup. And we say we give you 5 years time. In case your startup fails, come back and complete your third year, fourth year, and take your degree and go back. But at the same time, I would like to see a student after 2-3 years of taking a break comes back and tells me that, sir, I don't need your degree anymore. My startup is doing well, and I don't want to waste 2 years of my time and sitting in the classes and get a certificate from you called BTech, which may not mean anything to me. And this is what is the type of students that should come out of all of you. And I am sure Nano Jatha kind of events are to really inculcate that feeling inside you, that I need to really transform India. We call this initiative as Bharati, for your information. We call this as bold-hearted aspirants raising to transform India. That's the name that we gave. We want students, youngsters like all of you, to raise to transform India. India has to change that particular tag that it has been given to it, that you are a software country, or you are a sort of what is called service country, to a new tag where we say India is a technology country. India makes products which are sold everywhere in the world, is something that should happen. And who will make this? It's only people like you. So my request to all of you is, if any one of you is interested in some innovative ideas, in fact, this year we also did something. While between all IITs, we have what is called inter-IIT sports festivals that happen. First time we did a inter-IIT UG innovation festival, innovation meet, where we called all the 23 IIT BTech students, saying that if you have any innovative idea, come forward. We brought them, and then about 100 people came. They showcased whatever their ideas are, and finally about 5 of them were selected. About 15 lakhs of prizes were given to them. I would like to thank our BOG chairman, Mohan Reddy Garu, who sponsored that money, and we were able to do that. And we want to do this year after year. In fact, we even have a plan next year to start a new BTech program. We call this BTech program as BTech in Technology, Innovation and Entrepreneurship, where a student every semester, out of I do not know how many credits you do in a semester, typically at IIT Hyderabad about 18 credits a semester. Out of the 18 credits, 9 credits, half of it, you will do courses. The remaining 9 credits is to make a product. Okay, you will make a product every semester up to the end of the 6th semester. And 9 into 6, 54 credits is the theory that you study. In the whole BTech, you will only study those 54 credits. We are going to Senate to get this approved. And if that happens, and these 54 credits also, student will choose what he or she wants to study. I want to develop a 3D printed object. What is that I need to learn to do 3D printing? Okay, I will develop that. I want to develop a sensor. What do I need to do to develop a sensor? Only those subjects he or she will pick up and study. And this way, every semester the student decides something that I want to build, and the 9 credits will go to those courses which are essential for that student to build that. And in the final year, the student will not have any courses at all. He or she picks up one of those 6 products, and at the end of the year, the student will have a business model on how do I not only make a product but sell the product. It's also important making product. And we always say the difference between science, technology, and engineering. Engineering is to make a technology which is economically viable. Otherwise, it is not really valuable at all. It will still sit in your lab, but it will not be in the shops. If you want something, a product to go to the shops, you need to identify how to make it economical, the whole technology, and scale it up. Both are very important. So these are all, I think, are essential at your age, and we are trying to create an environment which helps in all this. I'm really happy to share with all of you that in the last 6 years, IIT Hyderabad students and faculty put together have come up with almost 300 startups, 320 or some such number I hear. And that 300 startups, the revenue was 1500 crores. They raised a revenue of 1500 crores. These are all students and with the support of the faculty. So I would urge all of you who are coming from outside the institution. There is one gentleman sitting there at the last. His name is Malla Reddy. He is the Dean of Innovation. And if you are interested to get a support of your innovative idea from IITH, feel free to write to either to him or to me, director@iith.ac.in. We will connect you to the right professor who will possibly mentor you. We can give space in our what we call it as TIP. We have a building here called Technology Innovation Park, which is a 1.5 lakh square foot building. Very few institutions in the country have such a space, large space for startup ideas. We want you to come up with such things, and we will also try to see how do we provide funding for your brilliant ideas, and see that you turn out into a product builder and help the whole country to grow. In fact, we have a plan next year to start something called a new way of entering into IITs through what we call it as builder's quota. Okay, where we say, okay, you finish your JEE Advanced, which is essential for joining IIT, but I will not take you based on the JEE Advanced rank. I'll ask you, have you built something in your school from 8th grade to 12th grade? Okay, anything. And have you competed in some kind of national level innovation competitions? There are so many such competitions are going on. And if you have done that, you're welcome to come to IIT Hyderabad. Okay, and now we are even planning to see if we can conduct some kind of a hackathon for them, where we'll give them some tools and tell them, I'm giving you this much time. You build something and show me. Okay, and from those we'll give some marks to them and create a separate merit list only based on the marks that they get through their building capabilities, and give admission to supernumerary seats in every branch. We're planning to take about 30-40 seats like that. We have about 15 branches of engineering, and we would like to see, we call this as builder's quota. Imagine 10 to 15 IITs decide every year to take such kind of students who have aptitude to build and at the same time capability to build things. You will see every school will transform. Every science teacher will tell, in addition to preparing for your JEE, why don't you sit in the Tinkerer's lab? Every school has Tinkerer's lab, but very few students go to Tinkerer's lab. And to be honest with you, many of you who might have prepared in Narayana Chaitanya, if you have, you would notice that you have never gone to even a lab. You have never possibly even touched a pipette or a burette. And got some marks, possibly pass marks or whatever it is required in that lab. I'm sorry to say this. This is all happening all around us. Okay? I want to see the whole school atmosphere, because I think if India has to be built once again as a country where technology grows, including nanotechnology, you need to do this from bottom up, not top down. From school level, students should get encouraged to build things. Spend time. Teacher should be able to say, spend time in your Tinkerer's lab. There is a seat waiting for you in IIT Madras, or IIT Bombay, or IIT Hyderabad. Okay? And that is a message that we want to give through this, what we call it as builder's quota. And I'm very confident that we will be able to start this next year through a mechanism by which we are developing that mechanism of how to evaluate them, how to be able to give marks to them, so that there will be a separate merit list prepared just based on their building capabilities. So why I'm saying all this, friends, is to just give you a message that there is a great responsibility on your shoulders to make our country. I remember 1999 when I went to Japan. The only thing Japanese knew about India was about Indian curry. I'm sorry to say this. He was also there. Okay? And people should know much more than that. And the elephants and snakes is what mostly they know about India. But I am happy to say today, in fact, just about a few months back, I was again in Japan. I go to a Japanese restaurant, I still have to pay cash. I travel in a taxi, I still have to pay cash. And then I told them, yes, in India, we only use this. Okay? We don't carry cash. I don't have a wallet in my pocket anywhere. I don't carry my wallet. So we have developed. In that sense, definitely, India has developed in a big way. Even to a roadside chai fellow, we can give. People even say to a beggar, you can use this and give money to a beggar. So there have been things that are happening. I'm happy, but much more to happen. And you have to take responsibility and ensure such things happen. So all the best to all of you, and enjoy, as Prasad and Narendra mentioned, is a joy. I mean, I always feel research is a joy, learning is a joy, and that joy has to be really felt by each of you. And I'm sure that this particular event will make you feel that at the end of the day. Thank you very much.
Thank you for your inspiring words, sir, and also for setting the tone for today's event. So, beyond science, your words served as an inspiration for all the students present over here. So, at this moment, now we would be honored to invite Professor Narhari Shastri, Dean SRC, IIT Hyderabad, and an renowned researcher to share a few words with the audience. So, kindly join me.
Good morning, friends. Professor Murthy Garu, Professor Prasad, Professor Mallareddy, Professor Bhavani, Professor Venkat, and most importantly, Dr. Narendra, who has insisted that I have to come here. It's really very important, right? We are all scientists, and when we want to have enjoyment, where do we go? Pandagalaki, Jatralaki veltam. Yes or no? So, it used to be Indian Science Congress for a long time. Now they make it as a Indian Institute of Science Festival. I have seen, when I see this Jatara, which is Jatha in Kannada, it is very good, because this is where we need to have fun. Actually, the very process of making it is to, one word which I have a lot of difficulty to understand is work-life balance. For me, work is life and life is work. The Karma Yogi, if you want to see, we see one in front of us, Murthy Garu. He does not sleep and he will not let us sleep. Everybody knows he works for 50. We don't know whether he will call us at 11 o'clock or 1 o'clock in the night or 5 o'clock in the morning, and everybody wonders when he sleeps. The next person is Professor C.N.R. Rao. We will compare. So, for me personally, one of the greatest scientists is Michael Faraday. In 1856, the gold chloride particles, when he made, when the particle size is very different, its color is very different. The ruby gold, gold can be blue, and they are all preserved. Colloidal science is very much there. This is precursor to nanoparticles, right? Colloids and dispersion. Michael Faraday is an amazing personality. He has close to 500 publications and more than 400 are single author publications. Michael Faraday discovered benzene. Michael Faraday discovered electricity. The famous saying that when the Queen of Minister of Britain asked him what is the use of it, he has the audacity to say that, yeah, maybe after some time you can collect tax by using electricity. Without electricity, we cannot even think about it. And when I was a student, I used to wonder about this coal, graphite and diamond. They are all made up of carbon. But when we were doing PhD, at that time, buckyball has come, which is also made up of carbon. Then carbon nanotubes have come, single wall, double wall carbon nanotubes. It must have got a Nobel Prize, but its impact is very high. Then graphene has come, which is a layer of the graphite, if you want to say, a two-dimensional object. Now, after 2D, everybody is looking at the inorganic two-dimensional aspects, MXCs, the tungsten, where Professor Rao has done a lot of work. There are so many implications to this. I always feel that in 1939, there was an article by the chairman of the advanced school in Princeton that the usefulness of useless knowledge. When the knowledge was there, because about 100 years before, quantum mechanics, people used to think that that is useless. But now, 20% of world GDP is based on the applications of quantum mechanics. When I was a student, I used to always feel that from Sierkota, one rocket will go up and it will come down. It's all useless, right? Many people used to say that lots of fun is wasted. But now you see, India is a leader in space technology, communications. We are able to use, we are way ahead of other countries and is able to be economically stronger, not only because of Chandrayaan, because of various discussions. Under the leadership of Professor Murthy Garu, we are also having lots of interest. There was a meeting on space technologies, how we can use it. So when we were doing PhD and other things about 30-35 years, Prasad, he used to do MSc at that time and we know each other. And Malareddy is a little bit junior to that, but he is doing much more important work on polymorphism and in pharmaceutical industry. At that time, there are three technologies which were very important. We used to always call it as IT, BT, NT. Information technology, biotechnology and nanotechnology. The nanotechnology, this is about 30 years before I am talking about. When I see the new theme, nanotechnology, the theme is AI and beyond. AI has come. Actually, people will say that when we were suffering from COVID, it is decided before COVID and after COVID. But I always say that the world is before ChatGPT and after ChatGPT. Things have changed quite a bit in 2023 March. The AI, generative AI and agentic AI systems, and IIT Hyderabad is now conducting a 3-day meeting from tomorrow onwards on AI and how AI technology is transforming. We all have to enjoy. Where do we enjoy again? Jataralu, festivals. Now this Jatara or Jatha in Telugu, you try to have fun. It will be a lot of fun for you to have this, and I particularly like Prasad's statement that don't be in the same college, the teams. When he made a statement, I saw some students, there was a very, very depressive look on their faces. But this is very important. You can get more friends, and this is very good. And elements and particles behave very differently. You can try to take anything from organic molecules to metals to inorganic molecules, they behave very differently. For example, if you take water, it behaves very differently. The anomalous diffusion of water at critical point, the phase diagram of water. and how water molecules behave inside a wall and outside a wall, nobody knows. People say that water is probably the most studied and least understood subject. Even now, about 8 years before, there was a paper which says that it requires about 28 to 29 water particles to make a water ice crystal. Still a lot of work is going on, and how this particular small liquid behaves, why it is very different from the other hydrogen bonded systems like methanol and ethanol, what is the secret for the latent heat of vaporization and other things, are still not understood. So now people are looking at molecules, clusters and materials, the continuum. Under the leadership of Professor Murthy Garu, we have a very, very good in situ microscopy facility which is there. We will be able to observe how molecules and clusters and materials will behave at atomistic level. You guys have to have the curiosity. Please have fun and enjoy. Thank you very much.
Thank you so much, sir. You surely inspired the audience sitting at the back. Continuing with the session, I would like to call upon Professor C. Reddy, sir, Dean Innovation and accomplished researcher, a leading crystallographer and a pharmaceutical researcher. So kindly join us on the stage, sir.
Yeah, thank you so much. Should I use this or? Okay, very good morning, everyone. So as Narendra started, so we are going to have fun here, right? And if you want to have fun in science, you need to understand things at the molecular level. Okay, you need to understand at the molecular, at the smallest level, and even if you understand at the orbital level, and then you will be able to understand everything. And there is a lot of computation that is being used, and we have Professor Bhavani Shankar here. He uses basically computational techniques to understand things at molecular level, then at the system level. Okay, then now we are talking about using AI and many tools for designing materials and material properties. Okay, so we are basically going very fast into that, and nanomaterials have emerged as very important materials in pharma and many areas. Okay, and so today you are all going to basically not only here but also going to try out a lot of things and going to have fun. So if you want to have fun, also always keep it in mind that you have to understand things at the molecular level, and once you start working on things hands-on, then probably you will be able to build new things and innovate. Okay, and our Professor Murthy has been pushing very hard, everyone, and I'm sure Professor Murthy Garu, many parents might be worried when you say that you have to drop out, and then if you say that you have to build, and he has seen the world. I mean, he can visualize and he has a vision, but a lot of people fail to understand. Okay, and here more or less we feel like sometimes parents at least feel that we are spoiling people, and Professor Murthy is leading that, and we are all helping him. And recently he managed to, he always says that students should drop out. I want to see a student dropping out from the BTech and then starting own startup, and many people will be definitely worried, right? And he is spoiling the people, and recently he managed to spoil one student. I will just read out his email. So his name is Chavan Rushikesh. Professor Murthy, you might be remembering him. He wrote last year in August. Okay, he is a 23 batch student. Okay, he wrote last year. That means he is in second year probably. He wrote that, dear director sir, I hope this message finds you well. I am writing to bring to your kind attention an urgent matter regarding my bona fide certificate. Okay, that means he has already decided to go out, and he has written to him to expedite the bona fide certificate. So then he continues to write, my startup FinStocks AI. FinStocks AI, stock market. Fin means financial. You can search, actually, you will find his website when you find them. FinStocks AI has recently raised a grant and has been selected for incubation at Draper University, San Francisco. San Francisco is a very much happening area. And then he writes that I am funded by Mr. Tim Draper. Tim Draper. Okay, you know who is Tim Draper? So he is introducing him to our professor Murthy, who is a first venture capitalist in companies such as Tesla. Okay, you all know Tesla, right? Elon Musk's company. He was the first venture capitalist who invested in Tesla. Okay, much before everybody knew about Tesla. And then also Skype. Okay, and Dropbox. You all know Dropbox, Skype, Tesla, everything, right? He was the first VC who invested in these companies before these companies became famous. Okay, and over 40 other companies he invested. And he invested in our students, Rishikesh Chavan's company, when he was in second year of his BTech, and he is been properly spoiled by our director, and we have been helping him to do that more and more. With this, I wish all of you and have a good time.
So, I mean, we can specs. So, thank you, sir, for your encouraging words and valuable insights. I hope everybody must be inspired in the audience. So now it's time for the keynote lectures, and first I would like to invite Dean SRC Professor Narhari Shastri to come up on dais and introduce our first keynote speaker of the day, Professor B.S. Murthy.
No, give me 1 minute. It's okay. I don't need this. Okay, thank you. So, Professor Murthy Garu was in IIT system for 33 years. Immediately after his PhD from IISc Bangalore, he was in IIT Kharagpur for 14 years. Then he came to IIT Madras for the last and worked for 12 years or so. Then he joined as IIT Hyderabad as a director, and it is his second term, and we are very fortunate to have him. He works in high entropy alloys and non-equilibrium materials, and he is a fellow of all the Indian academies and fellow of Third World Academy of Sciences, of World Academy of Sciences, Bhatnagar Awardee, a J.C. Bose fellow, and the list is endless, and he will throw me out before he does that. I will go. And sir, the floor is all yours.
Nowadays, you don't need to introduce anybody, is what I believe. You go to Google, you can find out about anyone. Good. So, I want to share the joy of my journey so far on materials to a large extent, particularly this nanomaterials. This is, you want to put that. And this one, I need it so that I don't lose. Yes. Okay. The title of this presentation I stole from Feynman. All of you possibly must have seen a similar statement which Feynman gives. There's plenty of room at the bottom when he gave that famous lecture. Right? You want to say it? So, when you talk of nano, okay, it's important to understand how materials are at nanoscale and how do they influence the properties of materials. And once you know this connection, are you not able to hear me? I think it's okay. These are all too many ornaments, very difficult to wear. Okay. Okay. So, and that's when you can design new materials. Understanding the materials at a small scale and their relationship with the behavior of the materials are the two crucial things which have led to a variety of nano products and about which I am sure BLV talks about it. What is interesting that the three other people other than me who spoke so far, they are all chemists. They all come from the same university. Okay, University of Hyderabad. Okay, of course, different time scales that they have come, and I am completely different from them. While people say metallurgy also has originated from chemistry, I do agree for that, but I am a metallurgist. I'm an engineer. Okay, and but then my joy of understanding materials at the small scale started with IIC Bangalore, where I started touching the first electron microscope in my life. And then since then, now 40 years, I have worked on so many microscopes. And it's always good to see. I used to bring school children and show them how atoms look like in a transmission electron microscope. Isn't it really a joy? So let me share some of those. And in all this connection, I should tell you, materials have evolved over years. Okay, so materials are generally divided into metals, okay, and polymers, and then ceramics and composites, combination of all these. Long back, starting from BCs, how we used to have stones, which are nothing but ceramics. We used to have wood, which is again nothing but a polymer. And of course, there were no metals at all at that time. Slowly metals started coming in, and by the time we came to the First World War and Second World War, the metals became very prominent. The steel, the aluminum, all of these. When people wanted to make aircrafts, aluminum became very important. And again, if you come back to current era, you will see more and more of composites leading the world. But there has always been a curiosity in people. How do atoms are arranged in materials? When we look at things like this is sodium crystals. If you actually magnify any salt particle, it looks like a cube. And people wanted to know how atoms, we know sodium and chlorine, how, if you want to call them as the ions, the sodium ion and chlorine ion, how are they arranged in the lattice of a material? People did not know those days. And they used to see this external form of the materials and think that possibly the internal atomic arrangement has something to do with the external form. Similarly, people have seen these snowflakes. These snowflakes, Kepler made them very popular. And many people used to work once upon a time, what is the shape of a snowflake? And slowly people realize that it grows in a hexagonal form. And then much later people came to know that H2O molecules, if you put them together and they arrange themselves actually in a hexagonal structure. So all these are like external morphologies giving an indication of what is the internal structure. And people have typically divided materials into two forms. One, they said they are crystalline, and second, they said if they are not crystalline, they are amorphous. And they look like this. If I use an X-ray diffraction pattern, does this work? No. Okay, fine. So if you look at an X-ray diffraction pattern of a crystal, it will show a lot of peaks, and each peak has some meaning. We understand those meanings, and from that we try to find out what crystal it is. And if you do an electron diffraction, you see this rangoli kind of a patterns, and these rangolis will give us an understanding of what structure it is. And if you go to an amorphous material, it gives you a broad peak in an X-ray. And if you do an electron diffraction, you see a kind of a halo. If you have ever seen a full moon day, many a times on a clean sky, you would see a halo around the full moon. Okay, the halo comes because of the scattering that happens. You have a variety of possibly even dust particles or so, which are, there is no crystallographic arrangement there. As a result, you see a diffraction coming from there. Suddenly, somebody in 1982 looked at a material in an electron microscope and took a diffraction pattern. And unfortunately, this fellow is not working. Okay, forget it. So if you look at, no, it will not work. Okay. So if you look at this particular diffraction pattern and see, there are pentagons. Okay, and if you count around this particular a central spot which is called transmitted beam, you have 10 spots. Exactly. And such a diffraction pattern has never been observed so far. And this kind of five-fold symmetry is what we call it as, has never been in materials at all. People said this five-fold symmetry is a forbidden symmetry because people always believed that a materials to be called as a crystalline material, it should not only have a translational symmetry but also a rotational symmetry which has to go hand in hand. And unfortunately, only certain rotational symmetries such as two-fold, three-fold, four-fold, six-fold are considered to be compatible with a translational symmetry. But then in nature, you see a variety of five-fold symmetries all around. And now people are able to make crystals which have, this is like a dodecahedron and structures like this. And this is a man who looked at these in 1982. Dan Shetman, his name. He was working in Caltech at the time, and he was able to see. And he actually writes in his notebook. Those days, at least during my time, we were still maintaining a logbook of whatever we see. We used to note. He writes on April 8, 1982. He writes SAD means selected area diffraction. He says tenfold question mark. Said, I don't understand, why is this tenfold? And he kept on repeating it because a good scientist will keep on. Whenever a student comes to me and shows some interesting result which nobody else has observed, first thing that a professor will ask is how many times you have repeated. Okay, so he repeated, he always got. But then when he went to his own supervisor, he was doing postdoc at that time, and his supervisor said, there is nothing. He called them as quasi-crystals. And he said, no, nothing called a quasi-crystal that can exist. In fact, very famous chemist by name Linus Pauling, he went to the extent to say there are only quasi-scientists, there are no quasi-crystals. So that is a kind of ridicule, if I can use the word, which he faced. And his own supervisor said, Dan, you are bringing disgrace to our group. I request you to leave this group. And then his first paper, which he sent it in 1982, was rejected immediately. And then he did not leave it. And then he went to two mathematicians, Blech and Gratias, and asked this question to them: why is it I am seeing this kind of a symmetry in my material? It's an aluminum manganese alloy, first time he showed, which fumbles me. I'm not able to understand. Then they said, if atoms or molecules are arranged in a material, not in a periodic manner, but in a quasi-periodic manner. For example, you all must have heard of Fibonacci sequence. And if you can have an arrangement of molecules in a Fibonacci sequence in a material, he says if you do a diffraction from such kind of an arrangement, you do get a symmetry of this nature. And this was mathematically proved. And after that, in 2 years, 1984 only, his paper got accepted. And then people got so excited and people started working on this more and more, to the extent that in 1991, the International Crystallographers Society has said, now the definition of crystal can be changed now. Okay, what was the definition of crystal earlier? That a crystal is that which has both rotational symmetry and translational symmetry, was the definition. Now said a crystal is any solid having essentially a discrete diffraction pattern. Okay, and one person's work has changed the whole world. And it's also important for you to look at this. This is a paper published in 1978 from Banaras Hindu University, 6 years before Dan has published his work. And if you again carefully look at it, there is a five-fold diffraction pattern here. Okay, this is aluminum palladium alloy, that was an aluminum manganese alloy. But again, his supervisors, Professor Shastri, retired now. Okay, he was a student at that time. Professor C. Surinana, very famous metallurgist, settled in USA. He still does a lot of great research. And both of them went to their guides. Their guide did not believe him. Professor Anantaraman, very famous metallurgist, and he is a strong believer of the old time, I would say, school of thought, I can say. And then in India, when your supervisor does not believe in you, you tend to possibly drop off. Okay? And that's exactly happened here. Dan did not drop off, and probably these two dropped off. And as a result, we did not get a Nobel Prize, which Dan has got in 2011. Okay? So please, one thing that I want to give a message to all of you is believe in yourself. This is very important in research. When you are doing something, when you keep observing certain phenomenon in your research, and whether your guide likes it or not, you should be able to pursue it. Okay? And then one day, I'm sure you will be a great personality. And this interest to see things at small scale has been there in people ever since science started growing. This is a time when somebody made a microscope. This is the first microscope ever made. Interestingly, the person who made this is the same person who made a telescope. Anybody knows who made telescope? Galileo. Okay, so same Galileo makes this microscope also. First microscope is made by him, and people started using that to see things which your eye cannot see. Our eye has a resolution limit of about 0.1 millimeter is what we say, 100 microns. Okay, from a distance of around 30 feet. 30, 1 foot distance, 30 centimeters. And people started developing microscopes of this nature. Optical microscopes you would have seen in biology labs somewhere in the schools. And we can see this is one such famous steel microstructure that we see, being a metallurgist. And then technology started developing, and people wanted to understand the reasons for those. For example, suddenly in 1903, there is a gentleman by name Wilm. He wanted to make a light and strong material. Okay, aluminum is very light. Many of you know the density is 2.7. Steel is 7.8 density, very heavy. He said, can I make aluminum as strong as steel? Okay, and steel, there is a particular process we hear in steels that you can heat it to high temperature, quench it into water, the same steel piece, immediately it becomes very hot. Okay, we call this as hardening, we call this as heat treatment. And he said, let me apply the same thing to aluminum. He took an aluminum copper alloy and kept on doing this again and again. And he found that it always remains soft when you quench it. He didn't understand anything. So, and on over a weekend, people say, the story goes that he left the sample on the table, went for a kind of holiday, and came back on Monday, and he wanted to repeat the experiment once again. But before repeating, he wanted to check what is the hardness of this piece. And when he measured the hardness, he suddenly found that this material is much harder than what it was on a Friday. Friday it was soft, Monday it has become suddenly hard, as if some angel has done some great thing over the weekend. And he again, as a good scientist, he repeated this, quenching it and leaving it for 2 days and then measuring the hardness. Whenever he left it for 2 days or 3 days, he found the material is becoming very hard. He called it as age hardening. Okay, and immediately there is a company called Dural, which is an aluminum company, gave a name to such a phenomenon and such an alloy, and they called it as duraluminum. Many of you by now must have heard that every aircraft where you fly, the whole aircraft body is made of this duraluminum. It's an aluminum copper alloy which has been heat treated by a process of heating and quenching and holding it for some time, which is called age hardening, and it becomes hard. But nobody knew why it has become hard. And in fact, in the same year, Wright brothers have used that alloy for their first flight. And people did not know anything about why it is so, until something happened in 1932. A gentleman by name Ernst Ruska has invented something called transmission electron microscope. Okay, very recently, May 1st week, I was in Jülich in Germany, where there is a center called Ernst Ruska Center for Microscopy. They have 7 aberration corrected microscopies in one building. Okay, amazing place. But what is more interesting is when I was telling that we have an atom probe here, which is called a 6000 leap, where like a CT scan that we talk of a body, you can do CT scan of a material at the atomic scale and see where which atom is sitting. If this is an aluminum copper alloy, where is copper sitting, where is aluminum sitting? If I have a steel, where is carbon sitting, where is iron sitting? This particular microscope can show you in 3D. And when I told this, they don't have it. They have almost 10-15 years old version, which is called Leap 4000. What we have is Leap 6000. For your information, friends, there is no university anywhere in the world which has Leap 6000, which exists at IIT Hyderabad. Okay? When we bought it 2 years back, there is no university anywhere. Carnegie Mellon does not have it. Stanford does not have it. MIT does not have it. But IIT Hyderabad has it. So if you have some time today, please feel free to visit this lab, which is called Center for In Situ and Correlative Microscopy, where we have wonderful microscopes where you will be able to see interesting things. And with that, when somebody put a sample of aluminum copper alloy in such a microscope, they were able to see extremely fine particles. And this is a 500 nanometers. The thickness of each particle is about 20 nanometers. And 20 nanometers cannot be seen in an optical microscope. You needed a microscope of this nature. So slowly as technologies grew, there has been a demand to understand materials at the small scale, and microscopes started coming into picture, variety of microscopes. And I'll take a few more minutes to, there are other microscopes. This is called an AFM, atomic force microscope, where if you put your hand below an atomic force microscope, you start seeing, and magnifying it, you start seeing blood cells, you start seeing the DNA and the helical structure of the DNA and the molecules in the DNA. All of these can be seen now. These are all have been used, variety of such microscopes to understand materials. This is one such thing. I did not put IIT Hyderabad thing. This stays in my slide deck always. Okay, this is IIT Madras, an aberration corrected microscope, we call it as, where the resolution that you can achieve is about 0.6 angstrom resolution. Today, you go to our Sati Center, we have 2 such microscopes where we can demonstrate to you 0.6 angstrom resolution. The highest resolution anybody can obtain in any microscope can be seen here. But all these started with the understanding of materials on nano. Just now, our Shastri Garu pointed out about this exactly, that you take nanoparticles and keep on making their size smaller and smaller, colors change. Okay, and incidentally, many of these old churches in Europe, particularly, if you go, the windows, all the colors in the windows come from these kind of materials which are used as colloids. People use the term colloids there, and many chemists are aware of these colloids. And this is another such example of how colors can change. I am sure Prasad will show many of those. And then we go to Feynman. Feynman was very, very passionate about this, going deep into materials and understanding them at a small scale. And he says that we should be able to see things at a very small scale. And his lecture says there's plenty of room at the bottom. And he says, my dream is this. My dream is, can we come to a stage at some point of time in life where we can arrange atoms the way we want? Okay, which is exactly what people do with the scanning tunneling microscopy and things like that now. There are technologies being developed in all this. This is, he said it in 59, imagine. And for that to be actually implemented in life, it almost 1990 was the time when it, almost 40 years or 30 years it took for people to do. But what is also more important is to understand from our own ancient history As a metallurgist, I'm always proud of these two things which are there as images. This is one. People call it as rustless wonder. If you go to Delhi, it is standing more than 1500 years now without getting rusted. It is just a piece of iron. Okay, how a piece of iron can stay without getting rusted, there is a lot of story behind it. I will possibly talk at some other time. But more importantly, people have made in 2000 years back. When I was a BTech student, I was told steel was first made by Bessemer, a Britisher. But then when I came into IIC and met a gentleman by name Professor Ranganathan, who wrote a book on the legendary wood steel, my own supervisor, PhD supervisor, I came to know that steel was made much before the great grandfathers of Bessemer were ever born, 2000 years back. And it was called ukku. In the borders of Andhra and Karnataka, this steel was made, and now people call it as woods. And this has become so popular that used as a sword by many people. The Alexander the Great, the samurais have used it. It can cut a helmet into two pieces. But as a metallurgist, what I was very fascinated is that this steel has about 1.4% carbon. A steel with 1.4% carbon is very brittle. Metallurgists know. I have my students sitting there. Okay, and how do people take such a brittle steel and make it into the form of a sheet of metal by hammering it? How did 2000 years back they had a technology for this? Is an amazing thing to understand. But what is more interesting for people like all of us who are today talking about nano is when people have taken a piece of this from an exhibition, put it into a high resolution electron microscope. This is a paper 2006 Nature. And they see nanostructures inside the steel piece. Whether this was accidental or they knew this way of introducing nanostructures into a steel piece is something amazing to understand. A lot of people are working on it. But what is interesting is the nanostructures go all the way up to 2000 years back in India. Okay, while we all talk about them now. Then I will quickly run to another microscope. People wanted to see, can I really see atoms, okay, on a material? So far I have not shown you that, okay. And particularly people's interest was, can I see them in 3D? First thing started by understanding atomic arrangements in 2D. This is a microscope called field ion microscope. Incidentally, my own PhD supervisor did a lot of work on field ion microscope, and I never knew that I will also jump into this at some stage in my life. This gentleman sitting here is a gentleman from India, NPL, National Physical Laboratory, Delhi, and he was working with a great personality by name Muller, who is considered to be the inventor of field ion microscope. And they were struggling to see, they wanted to see on a catalyst. Many of us know catalysts are excellent materials, but the atomic arrangement on the surface of the catalyst makes a lot of difference on how that catalyst behaves. And they wanted to understand how atoms are arranged on the surface of a material, okay, so that their understanding about catalysts can become better. And in the process, when they were trying to see, they were not able to actually see a completely a good, high resolution atomic arrangement on the surface. Suddenly one night, this gentleman gets an idea that why don't I put some liquid nitrogen into this sample holder? And he knows that if he tells his professor, he will not allow him to do it. So on a Saturday, Sunday, when he knows that Europe, usually Saturday, Sunday, no professor comes to lab. Okay, we all go. That's a different thing. So he utilized that weekend and happily put liquid nitrogen into the sample holder. And he suddenly saw in front of his eyes this. Okay, this is an atomic arrangement on a platinum. Platinum is face-centered cubic material, and it is supposed to have a four-fold symmetry, and you can see the four-fold symmetry amazingly coming out. Every dot that you see is an atom, image of an atom, shown by a field ion microscope. And then people started doing a lot of work. My own professor wrote a book on this, Professor Ranganathan, and this gentleman is a very young Professor Ranganathan when he was a student. And then people started saying, okay, fine, but now can I understand similar atomic arrangement in 3D? And then a lot of things have happened, and we started calling it as tomography. Like a CT scan is a tomography, and this is we are talking of a atomic scale tomography. Okay, that's why it's called atom probe. A lot of history. And how does this work? This works. You first make a sample in the form of a sharp needle and use a laser or a field to pull out an atom from the tip of the needle, and the atom goes through something called local electrode, hits a detector, hits a reflector and comes to a detector. Wherever it hits the detector, the XY coordinates are recorded, and these XY coordinates give an indication of the XY coordinates of the atom in a particular atomic layer. Okay, layer by layer you knock out, and as you keep on knocking out, this detector keeps on collecting the atoms. Okay, and the time that it takes from the tip of the sample to the detector is decided by the mass of the atom. This is simply mass spectroscopy. Many of you know. Time of flight measurements is what people call it as. And using the time of flight measurements, now you can reconstruct all these layers and then create an image which gives you an understanding. But you have to prepare such a sharp needle. Those days we used to do electropolishing to prepare such needles. But now you have techniques such as field ion FIB, we call it as, okay, focused ion beam technique, and using a focused beam ion technique, even a sheet of metal can be converted into a sharp needle. I'll show you how it is done. Okay. No. Take this. Escape. There's a video here. I'm sorry. This video is not coming out. I'm sorry. Perfect. So this is a small video. It will give you how such samples are made even from a sheet of metal. Let's say a sheet of metal, you identify a region, and using the ion beam, you dig everything around that region and make a cantilever kind of a sample. And then bring something, sample holder, weld these two and cut this piece here. Now a cantilever is lifted by a sample holder, omni probe we call it. Bring it onto an array of posts, we call them as sample posts, and put it on top of it, and again weld there and cut another piece. So this is like a 2 micron by 10 micron kind of thing. You can use that for making at least 5 samples like that, and then use the ion beam to sharpen this. Okay, like a pencil, you take a blade and sharpen it. This exactly does like that, and you generate a sample like this. And now the atomic arrangements. So this is how you keep a sample, a sharp needle, and then you have a local electrode and a detector and the samples. The atomic, what I would say, ions are collected. I'll stop this. Okay, so I will not go into the details of what I did long back, but we have set up a IIT Madras to begin with. Day before yesterday I was there, 3 days back. 2017 July 16th, we have set up something called National Facility for Atom Probe Tomography with the support of 8 institutions, which all gave me about 2 crores each. And then I went to Professor C.N.R. Rao. Okay, I will not forget about this great gentleman. He says, Murthy, I give you 5 minutes time and 5 slides. The moment you put the 6th slide, your project will not be sanctioned. So I was able to convince him that this is going to be a great facility in the country. This is the first atom probe in the country that we have been able to bring. And what is more beautiful about this microscope, this atom probe, is that we can remotely operate it. I convinced all these guys whose logos are all there, 6 IITs who gave me 2 crores each. There's an institute called ARCA which gave 2 crores, and then DST gave, DST Nano Mission is Professor CNR Rao heading that Nano Mission gave this money. And I have been working very hard for 2001. I came back from Japan to India after being the first Indian to have operated an atom probe. And 15 years I have worked very hard to get such machine to India. It costed us around 25 crores, but then it is not easy to get such a large money. And finally I asked the company guy, there's only one company which makes it. I asked him, can you make this remotely operable? He said, sir, give me 6 months time. I will demonstrate to you. So I still remember 2015, August 25th, he came to our IIT Madras, sitting in our MSB 104, our seminar hall. He was able to connect his laptop to the machine which is sitting in Alabama, and was able to not only align the sample, but collect atoms and demonstrate this. I invited my director IIT Madras for that lecture. And I told Professor Bhaskar Ramurthy, Professor Ramurthy, see this works. If you give me permission, I'll go with a begging bowl to every IIT. I visited 15 IITs at least, and tried to convince every director. Every director says, convince my material scientist, then I get convinced. So this job, I did it for 1 year. And finally, we got 12 crores. And then I went to Professor CNR Rao and explained about him. He was so convinced. Once he is convinced, that's it. He convinces everybody in the committee. That is what is Professor CNR Rao all about. Okay. So, and I got 25 crores from him. That 25 crores plus these 14 crores put together, we have set up a center which had all these. And what is more important is, this is the first in the whole globe, the first remotely operable atom probe. Okay, where we told all these people, you treat it as your microscope sitting in our institute. You send me a sample, we will polish the sample using FIB and put it in the microscope. Then we give a connection to you. You sit in IIT Bombay, operate it. IIT Kharagpur, IIT Kanpur, every one of them were able to sit in front of their computer and then operate the machine, connect to the machine and operate the machine. And we were able to do. We used to run it in 3 shifts actually. So a lot of amazing things have been done. This is, for example, this is a sample of a steel with nanoparticles in them embedded. Each of these pink colored dots are all iron atoms. Okay, and what you see, these green small patches, each of them are about 2 nanometer piece particles, and they contain yttrium, titanium, and oxygen. This is yttrium titanium oxide kind of a thing. And we were able to demonstrate. You can actually see how the atoms are distributed in all that. I will not go into the details. We also, this is how it looks like. For example, in a steel containing oxide particles, if you look at what is called elemental maps, each of them is an elemental map. This is a chromium mapping, this is a tungsten mapping, this is an iron mapping, and this is a yttrium mapping, titanium mapping, and oxygen mapping. And it shows that these are all very uniform, whereas this, you suddenly see that in a small region they are all concentrated. We can find out at the atomic scale what is the percentage of these elements that are present in these particles. So like this we can do a lot of such things. I will possibly jump and say to you that variety of materials can be studied by this. Anything which is a solid, what I cannot do is put inside an atom probe is a liquid. Other than that, anything can be put. And at the same time, I can also put a live biological sample. Okay. The reason is, in an atom probe, because I am trying to measure atomic positions, the positions have to be frozen. You know that at any given temperature, atoms keep on vibrating. Okay, this is the nature of materials. And based on that, we talk about entropy of a material, variety of them, heat capacity, everything. So if you don't want atoms to vibrate, you have to cool the sample. In an atom probe, we cool a sample to 20 Kelvin and see that all the atoms are more or less frozen, kind of, so that you will be able to get that. So that's the only reason. Live samples, once you cool them to 20 Kelvin, obviously they will die. So you can see on a structural materials, which means mostly materials which have a lot of metallurgy related, people who work on spintronics, magnetic materials, ferroelectric materials, anything. Any sample can be put. And now at IIT Hyderabad, we have set up this. We call this as SysCom, Center for In Situ and Correlative Microscopy. We have about 9 microscopes. Each of them can do in situ microscopy. Okay, you can heat a sample to 1300 degrees centigrade. You can cool it to minus 150 degrees centigrade. You can subject to a sample to a tensile loading or a compressive loading. For example, a biological sample, how does it behave under stress? You want to understand. Many a times we say we are stressed out. What does it mean by stressing out for a biological cell? Similarly, for example, if somebody takes, let's say, cancerous cell, people say that if a cancerous cell is heated to 50 degrees centigrade, the cell dies. The whole concept is, people call it as hyperthermia. The whole radiation therapy is all based on this. But what is actually happening to the cell at 50 degrees centigrade? You will not understand unless you put it into a microscope, heat it to 50 degrees and see it in front of your eyes. What's happening to these molecules inside? Is it disintegrating? Is the cell? Or some kind of a deterioration is happening, or something else happening inside? We can do all that here. That is the reason why this particular microscope, when we have set up, we have even hospitals gave money. LV Prasad Eye Hospital gave us 1 crore. We have, Dr. Reddy's lab gave 1.5 crores. Bharat Biotech gave 1 crore. And again, similar to the previous IIT Madras experience, we went to around 20 people, got about 1 crore each, more or less. 20 crores we got it. 60 crores came from DST, and that's the reason why DST secretary is standing there. Abhay Karandikar inaugurated this particular center. This is what we call it as LEAP 6000 I was mentioning, which does not exist anywhere else. And we can do a lot of things. I think I will stop here. It's 11 o'clock. So variety of materials, any kind of materials we can put, and we have been really thoroughly enjoying it. And if any of you want to do research and are currently doing some research, jump into it, bring any material, we will be able to put it into the atom probe. And also not only that atom probe, the other 8 microscopes that we have, we should be able to demonstrate to you that you can do real high quality research. Understanding materials, as I started, at the small scale is essential if you want to come up with new products. So thank you very much, and all the best to all of you. Yeah, if you have few questions, maybe I have.
Any questions from students?
I have been always seeing that watch.
Including anything related to how you can associate with IIT Hyderabad, I'm sure Professor
Sure,
Prabhudev will
sure.
be very happy to take your questions. 1 or 2 quickly before we can proceed with the next program, because questioning is extremely important, and that's what going to be my title of the talk, the importance of asking questions. And we have been losing this habit of asking questions. Anything we hear, that's it. Yeah, please. I'm extremely happy that somebody has raised their hand.
Go ahead. I'm hearing.
Good morning, sir.
Good morning.
I'm from OU Chemistry Department.
Very good.
My name is Ravi Prakhya.
Thank you.
I want to ask you, how do we actually put the sample into the system, into the machine?
Yeah. So as I told you, first of all, you have to prepare a sample through a fib. Are you talking about atom probe? Okay. So first you have to make a sharp needle. Okay, and the needle is held inside what we call it as a sample holder. And inside the atom probe, there is a region where you can load this sample. Okay, and once it is loaded, it is evacuated. You need to have very high vacuum, 10 to the power minus 10 kind of a vacuum, so that there are no molecules which are getting deposited on the surface and creating a problem for you, because you don't want any false signals. You want to exactly know what are the elements present inside it and where are those atoms sitting. So that's the whole process. But when I actually did, long back, I am telling you 25 years back, 99 to 2001, we never had fibs in those times. So we used to do electropolishing and make a sharp needle through electropolishing, put it into a TEM first, transmission electron microscope, find out whether the region of my interest, let's say I want to see a precipitate. Those days what I was working on is working on some metallic glasses where certain quasi-crystalline particles we used to find. I wanted to see whether the particular element called oxygen gets enriched in that quasi-crystalline particle and stabilizes the quasi-crystalline particle. So unless the particle is very close to the tip, I will not be able to get enough atoms from the atom probe. As a result, I first put it into the TEM, see how close my precipitate is to the tip. If not, once again polish it, take it back. So all this we used to do those days. But now, thanks to fib, we can do a lot. In fact, atom probe, fibbing is the largest time taking. It takes at least 6 to 8 hours to do fibbing a sample. It just takes 1 hour to get fascinating results from your sample. So you need to have patience. That's what we always say. Microscopists need to have a lot of patience. And if you patiently make a good material, is as we say, garbage in, garbage out. If your sample is well prepared, you get a great results. Otherwise not. Okay, thank you. Come, we will see one more point without taking much time. We have set up here India's first microscopy training center. In fact, there is a company called JEOL, JEOL, which has given a microscope freely to us, almost 20 crores microscope. And with that, we have put their name, JEOL Microscopy Training Center, where we say we actually have at IIT Hyderabad, one more interesting thing for your information is we have something called OAT, Open to All Teaching. We offer the courses that we regularly teach to our students, to outsiders like you. Okay, go to Google and put OAT at IITH. You will see a website opening, and what are all the courses that we are running at IITH in a OAT mode. For example, every classroom more or less we have converted. I teach in one of the classrooms here, and we have cameras facing the teacher, facing the speaker, and the cameras facing the students and things like that. So we converted them into hybrid classrooms, and we can have physically a few students, virtually a few students. If anybody is interested in taking a course of that in that mode, you can register yourself. You have to pay about 5,000 rupees, and with that you can attend any course. So we are running microscopy courses in OAT mode. If you get a minimum B grade, we say you come to IIT Hyderabad. Stay for some time. It can be 1 month, it can be 3 months, depending on which microscope you want to get trained. And at the end of the training, we conduct a drive test. And if you pass the drive test, we say you are an official user of our microscope. And once you become an official user, any time you can book your slot online and bring your sample, sit in the microscope, 2 o'clock in the night, 3 o'clock in the night. Nobody is going to operate it for you. You can operate it yourself. Even this, we can do it for you. So please make use of all these facilities that are available, starting from innovations to learning microscopes and doing great research. In fact, we have a number of internships available for people like you. Our departments are now slowly opening. Mechanical has started now. That BTech projects, you can happily come and do for 6 months project at IIT Hyderabad. We have even started bringing students from various colleges. We started with NITs at the moment that you complete 3 years of your BTech at your NIT, come to IIT Hyderabad for the full 4th year. We don't charge a single rupee to the student. We say you only pay for your hostel food and hostel stay. But we teach you whatever number of credits that you are supposed to go through in your university. We transfer the credits back. You get the degree from your college. But what is more important is that 1 full year you will do research here with a professor using all the facilities. I can tell you we have more than 500 equipment which are all cost from anything ranging from 50 lakhs to something like about close to 25 crores. Okay, so that is the kind of equipment that we have, and we want to use that. Most of the places where I go to NITs, I see people at the end of as I started, they are not seriously interested in research. We wanted to create that interest. First batch 30 students came. At the end of the 4th year, 25 of them said, "Sir, we want to join for PhD at IIT Hyderabad. Okay, and they join. Because we put a condition that you have to be minimum 8 CGPA to even enter here. And if you maintain that 8 CGPA at the end of the fourth year, you are welcome. So things like that we have been able to do. How to really inspire the students to do good quality research and develop technologies is the main purpose that we always have been struggling. And I hope all these efforts that we are putting in will be useful in the near future. Thank you very much. All the best.
Thank you, sir, for such an interesting and thought-provoking lecture. Now, I would like to request Professor Narhari Sastry, sir, to come on the stage and felicitate our director for the talk. So now I would like to invite Professor VLV Prasad to felicitate Professor Narhari Sastry, sir. So now I would like to request all the dignitaries to join us for a photo session outside the hall near the stairs. And after the photo session, I request you all to join for the tea and refreshments, which are arranged in the hallway. And after soon after that, we will join for the next lecture. Yeah.
11:30.
Uh,
11:30, sir.
11:20, let's say 20. Yeah. Mhm. So on the stairs.
They have already reached, so be fast, be quick. Welcome back, everyone. I hope you might be refreshed by now. So it's time for our next keynote lecture. I would like to invite Dean ITS, Professor C. Reddy sir, to introduce our next speaker of the day, Professor BLV Prasad sir, to the audience. So, sir, may we request you to kindly.
Yeah, welcome back, everyone. Now we are going to have the second keynote by Dr. BLV Prasad. And of course, you can find all the information in Google. He doesn't want the introduction, but when you search Google, so I'll tell you what you will find. Okay. So he's basically from Vijayawada. He studied in the school where Professor Murthy also studied. And then he did masters in University of Hyderabad School of Chemistry, then PhD also in the same place. After that, he did a postdoc in Tokyo Institute of Technology and then Kansas State, University in US. So in two places he has done postdocs. Then he has joined National Chemical Laboratory, where he is currently the chief scientist. And from 2001 to 2006, he was the director. Just recently, like last month, he finished his term very successfully and cleared a lot of problems in the institute in Bangalore. So this is called Nano and Soft Matter Science Institute, which is known as SENSE. So he was a director there. And so with this brief introduction, he has many awards, and I'm not going into the details. Fellow of 2 academies, and recently he was also awarded the CNR Rao Nanoscience Award. And with this, Dr. BLV, so stage is yours. Thank you so much.
Thank you, Professor Mallaredi, for that kind introduction. I also, another recognition I have is I am Professor Mallaredi Senior also, University of Hyderabad, and Professor Narhari Shastri Junior. Okay, so I think as I was mentioning during the last phase, is the crowd already thinned down? Some people have already gone after the tea. Okay, so anyway, fine. As I said, during the last part of Professor Murthy's talk, one of the things that we are somehow missing in these days is asking questions, right? Whether it is after the talk or when we read something, whatever it is, somehow this art of or the curiosity to ask a question is kind of coming down for whatever reasons it is. Maybe you are finding answers somewhere else, so you are not asking questions. But the title of the talk you can see is important of asking the first and the right question. Let me see whether it works. Okay, first and right question, and I will take the nanoscience and technology as an example. And as Professor Mallaredi was saying, I just finished my tenure as a director at this institution called Center for Nano and Soft Matter Sciences. And while right now I belong to this CSIR National Chemical Laboratory, this CSIR group of institutions are reasonably well known, whereas this DST institutions are less known, especially the smaller ones. So I may take a couple of minutes to introduce you to this institution called CENS. CENS is right now in this nice area. It is called, the area is called Nelamangala in Bangalore. And you can see this is the lab, this is the premises, about 15 acres of land. You see a lot of open areas. That is because we are going to have a new building coming up in this particular location. And this is where we have developed all the kits, etc. All the students who are taking the suitcases around the country are belonging to this institution right now. And to take you through the history of this lab was established in 1991 as with another name. This is one lab that has changed the name, changed the parentage, changed everything. So this lab was actually started as Center for Liquid Crystal Research. Professor Murthy introduced you to quasi-crystals, right? This is another field of research or another area which is very interesting. Liquid crystals. Again, when it was proposed, nobody accepted it. Liquid and crystal combining together in the same properties. By the way, where did you hear or where do you hear liquid crystals? Have you heard the word liquid crystals before? Yes, where? Teachers are going to remain silent throughout this talk. Okay. Anyone I see like a teacher, I will not come to them. Yeah. Course. Okay, wonderful. Any application that you think of? Okay, LEDs is not liquid crystal display, right? LCD is a liquid crystal display. LCD, right? Whenever you see LCD, there are liquid crystals inside that display. So LCDs were kind of prelude. Even in LEDs, there are liquid crystals, but it's a layer that is behind the diodes, basically. So these liquid crystal displays are one of the greatest examples of an application of liquid crystals. And this particular gentleman shown here, Professor Sivaram Krishna Chandrasekhar, his name, is a pioneer in a particular field of research called discotic liquid crystals, right? Discotic, a disc-shaped molecule. Until his pioneering work, people thought only rod-shaped molecules will display liquid crystalline characteristics, but he is the first person who showed that even disc-shaped molecules, and that is why they name discotic. There is no discordance there. So it is basically a disc-shaped molecule that will display a liquid crystalline characteristics, is what he pioneered. And if you want to know little bit more about him, he is a great physicist, a great scientist by himself, but he is also a nephew of Professor C.V. Raman. He is a sister son of C.V. Raman. There are two nephews of C.V. Raman that were very famous. One is Subramanya Chandrasekhar. Have you heard his name? Subramanya Chandrasekhar. Where and how? Nobel Prize, wonderful. For what field of research? Black holes, right? Are the Chandrasekhar limit, right? He's an astrophysicist. He's also brother son of C.V. Raman, and this Sivarama Krishna Chandrasekhar is a sister son. Okay, interesting. So this is what this lab is all about, and this is the area. These are the areas of research that this lab pursues. What we call as horizontals and verticals. Basically, horizontals are our capabilities. We work in nanomaterials, soft matter, liquid crystals, and electrochemistry, some devices, and also scale up. And look, these are basically used for different applications like energy, right? Device manufacturing like sensors, etc. And also some scale up of nanomaterials and other materials that we make. Okay. So, and then one of the areas that is very interesting to me, or like very nice to hear, is these smart windows. Like this is not many places that this kind of work goes on. You can pay attention to this window. It sees it is opening, it's changing its state from opaque to transparent, right? Imagine these windows that you have here, if you can convert them into opaque completely by a switch of a button, right? Then you are no worried, like some people are walking behind, there is a light behind, you don't have to worry about it, right? Similarly, if there is a window that can have what is called a digital curtain, a curtain that is not there but appears like a curtain, right? Like let me play this video. You can see that here. You see a curtain rising and curtain coming down, and in fact there is no curtain, right? It's a very interesting manipulation of refractive index of a material that leads to this kind of thing. All these things are extremely simple ideas. How do you manipulate the refractive index of a material? And that's it. From that was born this smart window, right? And then there are other areas like these are called electrochromic windows that you are probably aware of if you have flown in a Boeing 787 Dreamliner. You will see these kinds of windows. These are called electrochromic windows, where the opaqueness or the color of the window changes by applying a small electricity. And these are interesting concepts that are all happening. And some of these small examples, especially this PDLC window that is being shown here, you will be seeing in the afternoon as well in a demonstration. And you can ask questions of how does it work. Okay. And like with that, let me move on to my title of the talk and then my topic. Basically, the importance of asking the first and right question. And as Professor Murthy has already introduced, this particular field of research, everybody, the particular field called nano, everybody associates with this gentleman, Richard Feynman, who has given a talk called There is Plenty of the Room at Bottom, and challenged people saying that, can you write, for example, the 24 editions of Encyclopedia Britannica on a pinhead, right? And a small Gundusudi, if you know Telugu, Gundusudi Monamida, all 24 editions of Britannica have to be written. And people have taken that as a challenge. That's how this dip pen lithography, as you know, has come up, right? And it is indeed possible now to write, right, extremely large quantity of information on a very small space, right? That's basically the challenge is all about, right? So, but I am not going to kind of go through that kind of a, his talk and then how is it related to nanoscience and technology. But Richard Feynman is also known as a very good teacher, extremely good teacher. Why is he known as a good teacher? Because he always apparently used to simplify the topics into analogies, right? Real life analogies. and that's what I will try to kind of copy his technique and use real simple analogies to explain things to you, right? So in that sense, this topic will be kind of a popular talk than a talk that has a lot of information. Okay, now, right, this is, I hope, we are from University of Hyderabad, and those days at University of Hyderabad there was nothing. So every Friday, Saturday, we were in a place called Lingampalli, seeing only movies, right? So I'll take you one movies clip to you, and then start my talk.
ఎందుకు ఏమిటి ఎలా అదేంట్రా
Have you heard this word? Enduku emiti ela. Right? This is what I am going to talk about. Enduku emiti ela of nanoscience and technology. Right? Right? Why, what, and how. Right? This is how. Yeah. So this is extremely important. If you know everything about a topic, enduku emiti ela, you will know a lot of information. Right? So let me move on. So now onwards, I will be asking questions rather than giving talks. Right? Giving a talk. So there are three examples being shown on the slide, and we are talking about nanoscience and technology. Therefore, my question is, which of these three I will be extensively using as an example in my talk, right? Am I going to talk about nano edge display, or am I going to talk about this car, which is called nano car, which is no longer existing, unfortunately, but it's a great car nonetheless, or these things called standard SIM, micro SIM, nano SIM? Answer, please. SIMs. Okay. How many of you think it is SIM? Hey, suddenly then like, what is this? Many of you said SIM, right? Why this anonymity? Like anonymity. I don't want to be known as the person who has answered. Again, a current trend. Everybody murmurs, but nobody wants to raise a hand. How many of you have said SIM? SIM. I am also raising a hand, right? Yeah, now some people are raising hands, right? But I heard definitely more voices than those people who have raised their hands, right? So, but as all of you and as I am, the answer is not, right? None of them. The answer is none of them. I'm not going to talk any one of them, right? But there is a meaning why I have put these three things on the slide, right? For example, when somebody is saying that this is a nano car, what is the meaning of this? Small car. Wonderful, right? So it's a small car. But again, is it the smallest car? What is it? What is the smallest car then? Yeah, toy car can be a smallest car, right? Correct. A toy car can be a smallest car, right? But this is the smallest car in its segment. What is the segment? It's called passenger car. Among the passenger cars, this is the smallest car, right? So that one meaning that we have to take from this slide or remember from this slide is that nano means small. Please remember that. Okay. The next one is this, right? So nano edge display, just leave it. This is a very interesting example. I always like it. So standard SIM, micro SIM, and nano SIM, right? So one of you, can you tell me what is the difference between these three? Size. Wonderful. Who said that? Again, nobody raises the hand. Right? Great. Okay, raise a hand. What is the problem? Okay, so what size? Size of what? What has changed in these three? They're and it has been drawn to the scale for a very important purpose there. Okay, what is the change? What is changing between these three? This is, by the way, biggest cheating on earth. These three names, no, is the biggest cheating on earth. What is changing? I have given the clue also. The size of the plastic is changing, right? But the SIM size has not changed. SIM size has not changed. Only the surrounding plastic, how much is available, is just changing, right? And yet, what we want to say for me, right? So you have to capture my movements, whatever it is. Okay, so for scientists or science and technology practitioners, what is nano? 10 to the power minus 9. Okay, luckily, like nobody followed that, right? So I will rephrase it. It is correct. Nano means for us, or nano is a prefix. Is it correct? It is a prefix. It is always, for science technology practitioners, it is always supported by a suffix. What is the suffix? Yeah, meter. You are all PhD students, right? I hope you are not. Oh, okay, you are not. Okay, great. So it is either supported by a meter, it is followed by a second, it is also followed by a gram or a kilogram, right? Either a weight unit, length unit, or a time unit, right? Otherwise, it is just a prefix and it is associated with a number, and that number is 10 to the power minus 9. Wonderful. Slowly some energy is coming out. Great. Okay. So this is what it is. Nano means small, unique, all that is over. Nano also means a prefix, and that prefix is associated with one number, that is 10 power minus 9. Right? Now let me take this forward and see what is, right, among these three. When we talk about nanoscience and technology, which is a time unit and a length unit and a weight unit, among these three, which one we associate with nanoscience and technology? Length. Why? Why not a nanosecond? Why not a nanogram is important or exciting? So what? Right? Okay. Okay. So please associate to my previous slide. We said nano means? We also said nano means unique and special. Now let us take these three units and see which one of them is small and special and unique. Right? Otherwise, there is no interest. Right? Let us associate. Like obviously, as you said, length is the most important thing. So now questions again. Right? In time units, is nano small and unique? Right? Let me take you through this answer. Then I will see how many of you can answer this. You are all able to see me, right? Right? How are you able to see me? The process, scientific process, I want you to explain. Okay, I will ask somebody said some corner light. Who said that, sir? Please. See, somebody is pushing his hand, somebody else is pushing. Very interesting concept. Okay. Yeah, please, sir. See, this is not an exam. This is what Professor Murthy has been shouting, crying, whatever you want to say. Spoil the kids. We want to spoil the kids, right? So don't worry about an exam, getting an answer. No use of it, right? Sorry. Okay. So light. What after that? What? Reflection from. Okay, so I will replace. Wonderful answer, by the way. Please clap for him. So, right? Light has to fall on an object, right? Now, you are seeing me means I am the object, right? And especially light, when it falls on a very nice reflective surface like this, it comes to you very nicely, right? Okay, all of even Bhavani is laughing now because he also has a nice reflective surface. Right? Anyway, for surface, nanoscientist, surface is extremely important, right? Okay, so you are not an okay, this is how we need to do science. Absolutely like this only, right? Okay, so light reflects from a surface and comes to you. Then what happens? This is the extremely, up to this we know. After this, somehow we miss the link. What is that one thing that happens first when this light from an object falls in your eye? What is that conversion? Falls on a lens. Like, no? Yeah, go further. I want to get to the answer. There is a chemical reaction that happens. And that chemical reaction is a very famous chemical. How many of you are chemistry students or who have studied chemistry at some point of time? Luckily, at least. Right? Very few hands are rising. More hands are rising. So what is that one chemical reaction that is going to happen in your eye that changes and that causes all that? After that, there is an electric signal sent to the mind through a nerve, etc., it's optical nerve, etc. But there is a chemical reaction that is happening. What is that chemical reaction? Anybody can tell me? Photoisomerization of what? Yeah, ulta. It is a cis-retinal to trans-retinal. Okay? It is a cis-trans isomerization reaction that happens. That is the first reaction it happens. Right? It is a cis-trans isomerization. A molecule whose two arms are like this will change the arms like this. right? It is a cis trans isomerization of a molecule called level retinol that happens, and that changes everything. Okay, so this transformation now, how long does it take? What is the time scale it should take for us to see a person, and then all our reflexes are here. A femtosecond is 6 orders of magnitude smaller than is here. None of you are, unfortunately, is a spectroscopy theory. Okay, theory person can do that, right? Okay, so if you ask him to do a simulation of a protein folding for a nanosecond, he will say it is too long time, right? He will not be liking to do that. He will say at best I can go to picosecond, right? So for him, nanosecond is long or big, right? Please understand that. Like, these are all relative things. What we think as small and big is relative, right? So similarly, for anything that is happening at a femtosecond, if you want to study by a spectroscopy, you need to have a probe that is faster than a femtosecond. Like if you are clicking a photograph of an object that is running, right? Your shutter speed has to be faster than that's running. Otherwise, it's a blurred image, right? So for something you are studying at a femtosecond time scale, you need to, we go by 3 orders of magnitude, right? Centi, milli, like this, right? Micro, then nano, then pico, then femto, then attosecond, right? What is attosecond? Again, how many of you are physics students here? Somebody who has studied physics at some point of time in your life? Nobody studied physics. My God, okay, somebody. Okay, in physics, right? This attosecond was in news in couple of years ago. For what reason? Molecules of water will be there. Have I given you sufficient information? If you think that I have not given you sufficient information, you can say that also. 18 nanoliters of water, how many molecules of water? Gram of water, it is the same, because water density is 1 gram per cc, right? Whether I said 18 grams or 18 ml, it is the same. So if I, now I said 18 nanoliters, not 18 ml. If it is 18 ml, how many water molecules? 18 ml water, how many water molecules? Avogadro number, right? If you are drinking 18 ml of water, you are exactly drinking Avogadro number of water molecules. Let me drink 18 ml of water now, right? So remember, this is an interesting reading, right? I'm molecules of water. I can exactly measure number of molecules that I am drinking. If I can exactly measure 18 ml. Right? Interesting. These are all things that you need to. Now 18 ml is this slide because this is an extremely important slide. We miss this point when we are talking about nanoscience and technology, right? So when you have a 10 power 17 molecules of water and make a droplet of water, that water will behave like water. It will not have any special characteristics. But you want to have special characteristics when you are talking about nanoscience and technology. And if you want to have special characteristics of the water, you need to have few molecules of water, 100 molecules, 1000 molecules maybe. Right? If you want to have 1000 molecules of water forming a droplet of water, you know how much volume that water droplet will occupy? Any guess? 1000 molecules of water, a droplet, what will be its volume? Okay. What volume of one molecule? One molecule, right? It should be volume of one molecule. You will also need to have empty spaces. You need to have the unit cell, all those things. But it is a good guess. Please clap for again, right? Okay, nice. So this volume of this drop of water will have a volume of a Jeptoliter. Have you heard this word Jepto? A company we know, right? Have you ever wondered why this fellow called his company Jepto? We did not care, right? Everything I feel has connection to science. If you want to study science, right? Anything that you see on the road, everywhere, right? I will come back to those things also. So has a connection to science. Jepto means 10 power minus 21. Jepto means 10 power minus 21. What is the difference between nano and Jepto now? 12 orders of magnitude smaller. Again, weight or volume units, nano is not small. That is the essence, or that is the message that I want to convey. But when it comes to length scale, something extremely important happens when it is 1 order of magnitude smaller than nano. What is 1 order of magnitude smaller than nano in length scale? Angstrom, right? So all the molecules, ions, whatever it is, atoms, all those radii are roughly in the order of 1 angstrom. Now you take 10 atoms of such, assemble them into a wire kind of thing, assemble them into, that will be 1 nanometer, right? 10 atoms assembled in a linear fashion, a wire of 10 atoms will be 1 nanometer in length, right? That's it. You are now dealing with few atoms. When you're talking of nanometer, you are dealing with few atoms. That's when special properties are conferred to the materials, right? So many different material properties are coming up. Oh, that's what I will come to that later. And it's a very beautiful statement. This captures all the essence of my earlier, whatever, Kantashosha, what we call. It's basically nano is a magical point on the length scale. It is not a magical point on the time scale. It is not a magical point on the weight scale or volume scale, right? Please remember that, okay? So then we move on to what are the different properties that materials possess when you change the material's size to a nanometer scale, right? It changes color, it changes conductivity, it changes melting points, light, everything is kind of changed, right? Crystals, crystal properties, something that is crystallizing in some phase or some kind of a lattice in bulk phase, it might crystallize in another phase at nanoscale, etc., right? And the what is called the specific surface area of a material also changes, right? Many people say that surface area of material changes. No, it is a specific surface area of a material. What is the specific surface area and surface area? What is the difference? Volume or weight, right? If it is area per unit volume or weight, that is specific surface area. That changes, not the surface area, right? Okay. So, because if you take 1 centimeter cube, obviously it will have a higher surface area compared to a 1 nanometer cube. But if you have 10 power 18 number of 1 nanometer cubes, then that surface area is higher. Okay. So, please remember all these things. Okay. Now, melting points change, right? This is unheard of. When we were doing MSc practicals, at least University of Hyderabad, we were really made to do good practicals. We were asked to recrystallize benzoic acid. You recrystallize benzoic acid and you have to measure the melting point to prove that point that you have really made a pure benzoic acid recrystals, right? And we were struggling. They were saying 102.4, if I remember correctly. It was coming anywhere 80 to 90, right? So many impurities were there, right? Now I can go and challenge my supervisors or teachers saying that, no, I made a nanomaterial. Because melting points change based on the size of the material. Right? For example, what is shown here is the melting point of gold, right? The bulk melting point of gold is somewhere around here, because this is melting point by melting point of bulk. It is 1 here, it is 1064 degrees centigrade. As you come lower, the melting point decreases, right? 300 10 nanometers particle will have a 300 nanometer 300 degree centigrade melting point. So all these interesting thing happen. And then, like, optical properties, Professor Murthy was mentioning about it, optical properties of noble metal nanoparticles, right? Especially copper, silver, gold, they change due to a oscillation of electrons, right? Collective oscillation of electrons, and that causes, this is called surface plasmon resonance, and that causes these noble metal nanoparticles to display beautiful colors, right? So, like, for example, what you are seeing in the top view graph is basically optical properties of silver and then going on to gold, and this is basically alloy of gold silver, right? Optical properties change. Not only that, emitting properties of semiconducting particles, these semiconducting particles are called quantum dots, right? Emitting properties, which, because the band gap can be engineered now, it can be increased or decreased based on the size, and therefore optical emitting properties of or emission characteristics of semiconducting nanoparticles can be changed based on the size. What you are seeing here is one material, only one material, but different colors. It is emitting different colors just based on the size of each particle, right? If you change that, the optical properties change. Beautiful, kind of exemplifying of properties getting changed due to size change, right? This is what is nanoscience and technology, right? So a bit boring now. Let us move to some more examples, right? Are we the first ones to understand that, like, this one? Obviously, many other, for example, nature understands this, but it doesn't name anything. Like, it is in nanoscience and technology. But there are many, many examples in nature that have displayed or that have nanoscience technology embedded in them, and that is shown in beautiful examples like this, right? So the first example everybody shows is a peacock feather. Okay, what is peacock feather made up of? Has anybody thought through what is peacock feather made up of? It is made up of, again, I will give you clues. It is made up of a protein and a pigment or a dye. Any guess? We also have the same pigment, same protein. Any more guess? Wonderful. Keratin, one. Then pigment. Keratin is a protein, right? Aishwarya Rai tells you to take shampoo with keratin. Then we know what is keratin. If the teacher tells, who cares? If Aishwarya tells, yes, right? Okay, next is melanin, right? Melanin is the pigment or a dye that gives black color. Unfortunately, I neither have keratin, I don't have melanin, right? I have only few smooth surface, right? Okay, so if you have keratin and melanin, your hair is appearing black. But this fellow has the same material. Why is the colors coming? Where are the colors coming from? Is there another material that is embedded in that is giving the colors? No, not the density. Size. Okay, good guesses. Now people are coming up with good guesses, right? It's actually, the answer is there. It is the arrangement of protein globules or keratin globules that is in a periodic fashion. In our hair, it is arranged randomly. In a peacock feather, by the way, all of us should be proud of, it is peacock, not a peahen. Huh? Remember that. Okay. At one point, we should feel proud, no? Let us feel proud about it, right? So a peacock feather, right, has these feathers which has keratin and melanin, and that is showing these colors because the keratin is arranged in a periodic fashion, right? I take this route of joking with people. I hope you don't mind this, right? Take it in a simple thing. Okay. So the peacock feather has this beautiful arrangement of the keratin in a very periodic fashion, right? And if I convert that into a cartoon, it's basically this. It is like this, a window, right? So there are these holes and then there are gaps. Both of them in the visible spectrum region. What is the visible spectrum? What is the region for the visible spectrum? 400 to 800, 700, depending on whether you read Atkins or Puri and Sharma or whatever it is, right? Okay. So and if you change the gap between them or the size of that hole, it basically acts like a grating, right? One color is allowed to come or not allowed to come, and like if you change it, another color allowed to come, and these two colors are the wavelengths either constructively interfere or destructively interfere, and beautiful colors emerge out, right? That's why these are called structural colors. There is no color, it is only a structural color. Because of the structure, there is a color, right? Do you see this in any of your normal life? Structural colors. Rainbow is a structural color in some sense, right? It's basically a prism, acts like a prism. Any other example? On many natural butterfly wings, many other places, structural colors are there. Have you ever seen a CD? Right? Have you put it against light? Does it show colors? Is there a color inside? No. Right? Have you ever seen, like, especially in all our roads, when a truck passes after a rainy day, right? Or our Hyderabad Municipal Corporation bus passes, there is a layer of oil on the water, and then you start seeing colors. Is oil colored? Is water colored? But where is the color? Right? These are all structural colors. Right? What is the use of all these things? What should we do? Right? Basically, one of our colleagues, in fact, no, Mr. Nadu is not here anywhere. I don't know where is he. So his senior has done this lab work. Right? And it is published in 2025. Very recently, they have taken polystyrene beads. Now, white beads you all make necklaces out of and then put it, right? So polystyrene beads, you arrange them in a periodic fashion and you can see colors. You see this film, it is not as beautiful as nature, definitely not, but you see this is showing different colors at different angles, 0, 15, 30, it is showing different colors, same film, right? When you tilt, something else comes. These are all structural colors, right? This is a beautiful example of a structural color, right, in the lab. And this is another example, lotus leaf. All of you have seen, right? Water falls on that and then it runs away. It doesn't stick to the surface or it doesn't wet the surface, right? Have you ever seen this example? Yes, it doesn't wet the surface, right? Then this is super hydrophobicity. I will come back to that. There is another example I want to show you, and this is about what is called a rose petal. You see this? Here also water is like a droplet, right? It is not wetting the surface, but yet, unlike a rose petal, unlike a lotus leaf, it is not running away. It is sticking to the surface. See, roses also have some signs. February 14, you can use them, definitely, but other times also, you can study them, right? Okay, so if you study rose, you might get some intuition about science. So, like, what is the difference between them? Scientists have understood that both are due to what is called a micro-nano hierarchical structure that is present on the surface. They may appear smooth, but they are not smooth. There is a hierarchical structure. And that hierarchical structure, if the gap between that hierarchical structures is very narrow, then it is called a Cassie-Baxter state. And if it is slightly larger, it is called a Wengel state. On a lotus leaf, it is a Cassie-Baxter state. Therefore, it doesn't wet the surface, right? On a lotus rose petal, it is a Wengel state. Therefore, some water gets into the grooves and pins to the surface. It is pinned to the surface. Therefore, the water droplet, it is still in the form of a droplet. It doesn't wet the surface. If you pour water here, it will wet the surface, right? So, what is the use of all these things? We have been kind of doing some simple experiments, not really scientific experiments, but simple experiments. This is a glass slide. Please pay attention. In our lab, you can see now on this glass slide, water is now. See this droplet? It has gone under and it is wetting. This is wetting, but this is not wetting, right? Okay. And then my student does something very interesting now. And all water is gone. What is the use of this research? Why should we do this? Any application of this research? Water resistant surfaces. Where all it can be used? In the car. Wonderful, right? Car, paints, right? Anywhere you can, especially in cars. I like that example, cars, right? So outside the car, if you are basically slightly warm or something and you apply a lot of AC inside, and then there will be condensation, right? Outside condensation, you can use a wiper. Inside condensation is very dangerous, right? That is when your driver holds one wheel like this and goes like this. And you're all praying, right? Please, right? Okay, save me, right? So you can avoid all that, right? And I was very happy or very surprised to see there is another example where this kind of research can be used, and that is in your kitchen. Can you tell me now? I have given you a clue also. In the kitchen, where can you use? Teflon dosa pan, right? So have you heard my talk previously? No, right? Oh, thank you. Right? Okay. Because everybody is answering now, right? Okay. So Teflon dosa pan, right? Dosa pan or non-stick tawa, right? So you have a non-stick tawa, and then they say that please don't apply oil, but we don't like our dosa without oil. So despite that, we pour a lot of oil and start heating. After some time, that so-called non-stick tawa becomes so sticky tawa that you have to dig the dosa. right? You basically dig the dosa, and then along with the dosa, some black material comes that is so tasty, right? Okay, so there was a research funding that was given in NSF by NSF, Professor Shastri, that was funded to develop non-stick tawa without using Teflon, right? So you see what is the interesting facts, right? That this is NSF, National Science Foundation in US, not by DST in India. That's a different matter for us to worry about. Anyway, what happens to that, it is a different matter. But this is how, right, you can see applications of nanomaterials in different fields, right? And once if you can probably master all the superhydrophobicity, one day, right, on Hussain Sagar Lake, we all can be done doing like this, right? This is a not created, no Rajamouli movie here. It is a real, right? It is a real movie taken off a creature called this lizard, which is known to walk on water because of a hydrophobic web foot it has, right? So this is what can possible. This is not there right now, but hopefully one of you will build and then get into IIT and display the technology one day, hopefully, right? Okay, let us move on. This is another beautiful example that I like, right? So people are now, who is he? Why you are saying only Vijaykanth? There should be something prefix, no? Captain Vijaykanth. Yeah, there are three, beautiful, ladies who are fans of Captain Vijaykanth. Unfortunately, this guy is no more. A very good hero. I have nothing against him, but this movie clip is very interesting. Please pay attention. If you want to enjoy, I can play you one more time, right? A villain, a rowdy inspector, is filing a bullet at Captain Vijaykanth. Bullet is traveling, hitting him, going back, and killing the fellow who has fired the bullet. Right? Okay. So now let us see two more examples. Normal cloth, fired a bullet, bullet pierced through. This is a lab example. This is no VFX again, right? This is a lab example, not by our group, somebody else. Bullet hit a cloth, is going back, right? Nobody claps now. For Vijaykanth, everybody clapped, right? For a scientist, nobody claps. What is this, right? So this is what is possible, right? And if you can do this, there are issues. I want to ask you during the afternoon, what are the issues with this technology, how to take it forward, what needs to be done else, right? Apart from the cost, everybody says that cost. No, there are technical issues. I want to come to you with those technical issues. So if you solve those technical issues, all the bulletproof vests our soldiers are waiting can be very lightweight, right? So these are the interesting examples, like very useful examples. This is the last example, and then I will move on with two, three more slides, and I will be done.
Is a piece of plain, untreated cotton cloth. Watch how quickly it is engulfed in flames.
This is a normal cloth, right? It is quickly catching fire, and this is one of the reasons why fire spreads so fast, especially even in hospitals with ICUs. There are people who have died even during COVID time.
Now, a sample treated with band fire.
So you see this cloth
never catches.
It never catches fire. It becomes black, right? It becomes like basically, it takes the flame, but never allows the fire to spread. Okay, it's a beautiful example of how nanoscience and technology. There are nanoparticles of some endothermic particles embedded in this kind of.
We'll even take a blowtorch to a common shop towel. 1400 degrees, and it still refuses to ignite.
Nothing happens to this cloth.
We understand what you're going through when.
So these are all interesting things. In this particular field of research, since 1980s, Professor Ruska, he was mentioning, Professor Murthy was mentioning about Ernst Ruska, and then these are the number of Nobel Prizes were given to one particular field of research, right? Nanoscience and technology. I have taken some liberty to add few names, but please remember, most of them have something related to nanoscience and technology, right? Either nanopores or nano whatever. So these are one particular field of research getting so many Nobel Prizes is not so easy, right? Which means that there is importance of this field of research, right? That is being pursued. Now we move on. Who started this? This is the question, right? Who started this, right? And Professor Murthy said, and all of us also agree that Professor Richard Feynman played a crucial role, but I believe he did not start it. And I'll prove you or I will show you examples at least to say that he did not start it. And there are other people, all of us write thesis reports, especially MSc students. Everybody starts. The field of nanoscience and technology research was started by a lecture. There is plenty of room at the bottom by Richard Feynman. This is a standard statement, right? In every thesis you find this statement, right? So is it really true? Have you really searched? Has he done to be called, right? So he has definitely contributed. Don't again quote me in Facebooks, etc., saying that Prasad said Feynman did not do anything for nanoscience and technology, and I am done, right? Tomorrow I am done. That's not what I'm saying. We need to understand how the field evolved, right? And then there are also people who say that he has really coined the term nanotechnology, Norio Taniguchi, but he also did not start the field, right? So who started the field? Let us see, right? These are the really, did they start the field of research, right? So this is a cup that Professor Murthy also showed. It's called Leicher Just cup or Leicher Just cup, whatever pronunciation you want to do. Let us not worry about it. There are two cups being shown, but there are no two cups. It is one cup, right? What is the interesting thing about this cup? This cup, if you shine light from outside and the light is coming back like a reflection, it appears green. Whereas if you put the light inside the cup and it is being transmitted, a transmitted light, if it is coming into your eye, it appears pink, right? Beautiful thing, right? And when was it made? It was made in somewhere around year 400, okay? It was made year 400. When it is made in year 400, today we are 2026. 1600 years ago, it was made, right? If it was made like this, it was mastered by the time, right? By the artisans. If it was mastered by the time, they would have been practicing it for some more time, right? At least I would say 100 more years, right? So if people have been making these kinds of cups and seeing these beautiful colors, nobody asked a question, how these colors are coming to the glass, right? Yet they were actually changing the experimental conditions. This is what we do. Somebody does something, we all do changes in the experimental conditions and find new things. New colors are coming up, right? Many new colors have been added to the glass making process, right? These are all stained glass windows. Professor Murthy was also mentioning. These are called stained glass windows. There is no color applied to the glass. The color is inside the glass. The glass itself is colored, right? That is the difference between normal glass and a stained glass window. So this is what the colors were coming, but nobody asked a question until I think again you were mentioning. That's what I said. Everything that I wanted to tell, Michael Faraday came into picture. Michael Faraday was the first person who asked the question, why these glasses are colored, or how are they getting this color? And if we construct a story, what would have he done is that he would have gone to a glass maker and then asked a question, how are you making this glass colored, right? So now another question, what are glass? What is a glass? What is a precursor to a glass, if I want to ask you? Silica, okay. Alumina, wonderful, yes. So borosilicates, if I want to put it as aluminosilicates. How do you know if somebody has not known this word borosilicate, but still if you have seen a glass, I would have expected you to ask a question. Why? Have you bought borosil glasses? Borosil, right? Have you ever asked the question, why these glasses are the company is named Borosil? Borosilicate, right? So this is a company that mastered the art of making glasses with borosilicates, right? That's why that company is called Borosil. Okay, so this is how that's what I want to tell you. Scientific temperament means this. See anything, ask a question. Why? Right? Then you will get a lot of information, right? So borosil glasses were made. By the way, Michael Faraday went to a glass maker, probably asked him, how does the glass get a color? So the glass blower would have answered, because we know the process. Now said that I am adding a metal salt while making the glass, right? What is the glass making process? You take these borosilicates, heat them to a particular temperature, quench them, and that's it, right? Glass forms, isn't it? What can happen? What is a metal salt? I think I have 10 minutes, right? 10:30, 12:30? Yes, yeah, okay. I'll be done, don't worry. When you are waking, standing up, I get worried. They are my masters. Huh? They can do whatever. They can drag me out also, right? Okay, so what would be happening? They are adding metal salts. What is a metal salt? Iron chloride. What is the formula of iron chloride? FeCl2 or FeCl3. What is this FeCl2 or FeCl3? What does it mean? Oxidation state. Oxidation state of what? Iron. Okay, if it is FeCl2, what is the oxidation state of iron? +2. If it is FeCl3, +3. What is this oxidation state means? Number of electrons that is less than what it should have. Right? So now Fe3 plus has 3 electrons less, Fe2 plus has 2 electrons less. Let us imagine, right, this glass maker is adding iron chloride while making the glass. What can happen to the iron chloride? Because there is a color that is coming up. They are adding cobalt, nickel, iron also, but noble metals, gold, silver, etc. But a metal salt is being added. Right? When you are adding a metal salt to a glass, what can happen to the metal ion now? Right? So 3 things can happen. That one, it can remain as it is, no changes. Second, it can get further oxidized. Third, it can get reduced. These are the only 3 possibilities to be. We have formed a hypothesis now. This is a hypothesis. This is a research hypothesis. Michael Faraday made this hypothesis. Now eliminate. If it is remaining as it is, the color should be like iron chloride salt. No, it is not that. Right? If it is getting further oxidized, is it possible? Maybe it is getting heated up, but it is very difficult to lose more electrons, one that has already lost electrons. So the only other possibility is that it may be getting reduced. Right? This is basically an experimental procedure. Let me now take a metal salt and reduce it. What do I see? He asked the glass maker, what are the salts, different salts you are adding? He said gold is one salt. Right? So he took a gold salt, added a reducing agent called phosphorus, red phosphorus, in a solvent called carbon disulfide, and that's it. Right? I think you are mentioning again, like the gold salt that is preserved. This is a gold salt that is preserved in musea, right? So you can see that, like the color of whatever is that. It is almost similar to that Lycurgus cup, right? Almost similar to, right? By the way, I don't want to really take long time, but please read about Michael Faraday. Anybody who is thinking that I am not privileged to have facilities and therefore I am not performing, one should read Michael Faraday. Right? No degrees, no nothing. Right? Extreme poverty, yet he has done wonderful things, amazing things. Right? Absolutely amazing things. Yeah, we should definitely, wherever he is, he should be our hero. He should be our hero. Okay, so this is what he did, and what I wanted to tell is, this is actually a few years ago, his research papers were analyzed, 450 of them, as somebody said, and they were all analyzed, and they have seen how does he write English, right? He is born in England, by the way, right? He is born, raised up, or whatever it is, in UK, and then yet you see his reading, his English, absolutely atrocious. He was writing all bad English, right? All spellings were mistakes. For him, writing is R-I-T-I-N-G. Why? We never pronounce W, right? So he never wrote. Who cared? So please understand, this is an important thing that we need to understand when you are studying science. Knowledge is important, not really the communications are good, important, but not so important, right? Please understand all that. Okay. So this is a slide that Michael Faraday made and proved the point indeed, right? If you make noble metal particles or you reduce noble metals under some circumstances, you can get colors, right? And he called them finely divided metal particles. He did not even call them nanoparticles. Again, who cares, right? So this is true, right? These are finely divided metal particles, right? So we are calling them nanoparticles, okay? That's why I feel that, and after that somebody took a glass slide that was made during that time, took it into a microscope that Professor Murthy was mentioning, and indeed they saw metal particles inside the glass slide, right? So I feel that's why Michael Faraday, of course, Roman glass makers, before that, as Professor Murthy was saying, Indians who made the Damascus sword, they were all inventors of nanoscience and technology. But Michael Faraday asked that question. Right? That is important. Please remember that. Okay. So now this is a chronology of what has happened after that, right? Since 400 AD. This is a slide that captures only events, but I wanted to put it in a slightly different perspective. Please pay attention to this. This is extremely important to me, right? This is what I want to convey to you. So when was that first discovery or first recorded thing of, right, nanotechnology? Year? When did he ask the question? What is the difference? Right? Okay. Then Richard Feynman, what is the difference? Then buckyballs, again somebody was mentioning, what is the difference? Then semiconducting nanoparticles, what is the difference? You see, first question took 1400 years to ask. After that, it is rapid. So ask questions, right? This is extremely important that we need to ask questions. Now we can't even imagine our life without a mobile phone, without a smartphone. This is a fuel cell bus that is running in India, right? On Indian-made fuel cell in NCL Pune. This is with KPIT. This is Professor Mashalkar, Ashish Lele, etc. So look, these are all happening now. We are seeing the benefits of nanoscience and technology in real life today, right? Because of all that question, I will say is important. I don't know how much time I have. There are two examples that I will just rush through an explanation. One they are saying is that all future will be printed electronics. They will not be made in fab labs. They will all be made by print processes, right? And for printing, you need a ink, and the ink will be made up of nanomaterials, right? That is one slide that tells, this is a video that tells that. In the second one, what it tells you is that, for example, as simple application as, this is an advertisement, but I am not a medical representative representing that company. Please, again, don't quote me like that.
90% डॉक्टर्स का भरोसा Savlon एंटीसेप्टिक जो जर्म से प्रोटेक्ट करे 8 गुना बेहतर. अब Savlon की सुरक्षा नए हैंड वॉश में.
What is there? Sorry, I think, yeah, silver nanoparticles. And then this is another example where again it has been shown that if you use nanoparticles and properly surface modify them, you can deliver drugs to the location where it has to be sent, right? Like an Amazon courier, right? You all want your Amazon courier to be dropped at your place, right? Like that, drug can be delivered to the location where it is to be delivered if you tag an address to that. And for that, the drug has to be either coated on a nanoparticle or to be in a nanoparticle form. Okay, so these are the new applications that are emerging, and right now these are all concepts. Some prototypes or some proof of concepts have been made, but future we might see all of them in reality. And this is 2 or 3 slides. Some preaching I have to do, right? So I'll do the preaching now. We are here, somewhere 38 is our innovation index in 2025. That is okay. We are doing better. But what I am worried about is even Malaysia is better than us. Lithuania is better than us, right? Malta is better than us in innovation index, right? This is what again Professor Murthy was mentioning about, right? So innovation is not really happening. And again, one of the slides that what is required. This is my own analysis, right? You may take it, you may not take it. It's up to you. There is a beautiful poem by Subhadra Kumari Chauhan, Tukra do ya pyar karo. It's up to you, right? So let me take you through that. To me, these are 3 important things. Clarity. Have clarity, right? Unfortunately, today's younger generation, again, to my opinion, are not having clarity. What they, right? They're cluttered, right? And everybody gives them advice. Everybody gives an advice, right? Including the walker by, hey, what are you doing? Hey, why don't you do this? And we hear them. Right? Everybody, we are such a, this one that everybody wants to give an advice. So this is what happens. And inside us, we all want to be unique, right? We want to be special. But when it comes to choosing a career, unfortunately, we become that. One fellow runs, we all run behind. Right? Today it is AML, today it is AML. Yesterday it was computer science, today it is computer science. All of us want to do the same thing. I don't know why, right? Okay, this is one thing that please don't let anybody take any decision for you. You should take the decision for you, right? Of course, it needs a convincing of your family, etc., but it's a different matter, right? Please do that, right? And this is one example that Professor Murthy was showing, right? So this is what he was mentioning. All of you, I don't want to take the names, they may sue me, and if they sue me, I am gone, right? They're all CEOs of big companies, you know them, right? And if you look at their career path, it is exactly the same, right? Microsoft CEO, Google CEO, whatever CEO, all of them are mostly Indian origin people. They all have the same career path. And these are our idols today. Definitely, right? Are they our idols or not? Let us be frank about it, right? They are our idols. They are doing absolutely great, no doubt about it. But have you ever asked, are they the founders of those companies? They are all employers of that company. There is a founder who is sitting somewhere, can fire this person. And who is that founder and what is his qualification or her qualification? Let us look at it. This is what exactly Professor Murthy was mentioning. Right? These professors may kill me again for spoiling their kids, right? So if you want to do something, you may have to sometimes drop out. Just don't get into this normal stream, right? You want to be different, right? This is what they did. They just dropped out when they found an opportunity, right? So do a calculated risk. Don't take, oh, because I said like tomorrow it was empty, right? They will not get their salaries and they will kill me basically, right? Don't do that. So that's not what I'm saying. What is important is that if there is an opportunity, if you have that, we are somehow risk averse. We don't take risks. We need to take risks, right? So including me, I could not take a risk when I was young. Okay, so last slide, and then I am really done. So this is what I want to tell. Have curiosity, right? Again, I'm a big movie buff. I started with a movie clip. I will end with a movie clip. This is a Hollywood clip.
Of Crispy Bear. A long time ago, this little bear was alive because she listened to her father, so she was happy. But Crispy had one terrible problem. She was filled with curiosity. Yes, and one day she saw something new and died.
Just like Dad?
Yes.
Same ending as every day.
We never had the chance to explore the outside world. But what we didn't know is that our world was about to change.
Hey, come down! Into the cave! Go! Look out!
You really need to see this.
This is again taken from a movie called Croods. If you want to listen to the movie, see the movie, please close your ears. I will tell the story now. Right? Okay. This is a story about a cave people. So they are all living in cave, and then the father always tells, "Don't get out of the cave." Right? That's what the Crispy Bear story. He says that the Crispy Bear has a terrible problem, and the terrible problem is curiosity. If you have curiosity, you go out of the cave, you will be killed. This is the story every day, and the granny says, "Same ending every day." Same ending every day, right? But that Eve, the girl, is very adventurous. She wants to see outside world. And she goes out. Of course, there are dangers. Cave is almost caving in. But still, when they get out, they see a beautiful world, right? It needs some adventure, definitely. But once you take that adventurous path, and if you are successful, always the end will be beautiful. So with that, let me end. And this is what we are supposed to do. This is Professor C.N.R. Rao addressing such people long time ago. But we are now trying to do it in across different places. When all people come to Bangalore, it is like this. But because now we cannot do that, we are going wherever people are there and doing that. Thank you very much for your attention. Only if we do that, we should be called Vishwaguru Bharat. Again, I will be happy to take one or two questions if you have. I think, where is Monit? Monit, right?
Yeah.
12:30. Fine.
Yes, I think you're absolutely on time.
Yeah.
So thank you so much, sir. That was most wonderful and interesting talk. And I'm sure the audience had a great time. They might have learned a lot of things today. And the stage is now open for the questions, if you have any questions for sir.
Yeah, I'm here. I'm not running away or anything. So just tying my lace. Some questions, please. Otherwise, what is the use? Again. No questions? Yeah, please.
Is also second part. The first part, one very nice way of presenting the length scale.
Yes.
I was wondering why I never had a chance to listen to you. Because there is a time scale presentation.
Absolutely.
There.
Yes,
I did that one.
Exactly. Yes.
And how molecules move.
Exactly.
And what is the time scale.
Time scales, exactly. Yes.
So this is very much synonymous. Maybe, if any time
Sure.
they can hear that one.
Absolutely.
And
yes.
any chemical reaction they see,
Exactly.
they cannot feel that one.
Exactly. Yeah. Sure.
And the way from nanosecond to femtosecond, there is exactly the time scale of reactions.
Exactly.
Thank you very much for your.
Yeah, sure. Yeah. Thank you, sir. Any questions from students, please? One question? Yes, thank you. Yeah, I really appreciate you. I will take a selfie with you. Right? Nobody else gets a selfie with me now. Only that guy gets a selfie with me.
Sir, how did humans figure out how to measure time at the femtoscale?
Oh my God. Okay. So this is a tough thing for me, but maybe a physicist can answer. But for everything, you need to have a standard, right? There is always a calibration that you do, right? So first you do that calibration, and then you probably either extrapolate or interpolate, and then get it. So there is a time scale that is associated with something. You may observe something. For example, how does sun rise and then sunset? So these are the things where started, right? 24 hours. So that's how. Well, otherwise, time is a kind of a relative phenomenon. It's not a right. Yeah, it's a relative phenomenon. Yeah, Professor. Yeah. So what we say is relative, right? Here, what is the time? There, what is the time? It's all different, right? Yeah. Anything else? Yes, please. Yeah. Mm-hmm. Wonderful. Yeah.
Published in the flame retardant field of area. Like recently only, I'm a chemical engineer. Like my in field of domain, I want to advance in the AI/ML of sector. Like my motive is to introduce AI/ML in chemical engineering in such a way that in a industry, most of these things are automated. I can be without doing experimentation. Like as we all know that experimentations are costly due to many field things.
Asking the wrong person anyway. Yeah, go ahead. Go ahead.
So, like recently in the mini project, I had developed a AI model using where I had like in the starting phase, I had made considered two things like a emulsion nanomaterial and a solvent. I had developed a model to it's a simple model using the Python coding and etc. The success rate was nice, like around 0.97. And again, I had through curiosity, I had again done multiple experimentations. Like emulsion nanofluids is used in a heat exchanger to enhance the heat exchanger properties. So like I'm still working on it. Like I had done the experimentation with multiple emulsion nanomaterials and multiple solvents. The outcome was very well. Like I want to ask in a curiosity way that how I can more develop in it.
Okay, no. So I think first thing is how did you train your? That is what probably first thing needs to have. What is the data set that you had to train your?
Like
right?
sir, I had
no, don't answer me now. It became a talk, right? Please look at that, right? What is that data set? Many a times I feel is that people are not taking the proper data set to train your system, right? And then you can develop whatever it is. And obviously after that you need to test your system so that again you can refine. So if you are doing flame retardant materials, I am sure there is some set of data that is available. Use that data, train your system properly, and then use that to validate. And ultimately validation is only through experimentation, and that is physical experimentation, not in a computer, right? So sorry, Bhavani, even if you don't like it, and Professor Shastri, right? So you need to validate it, right? So have you validated your results?
Like sir, the model is ready. Like my major.
No, have you validated your result in an experiment?
The major project going which I am going to.
Good. Congratulations and all the best. Yeah, thank you. Yes, please. Yeah. చెప్పండి
మనము ఇప్పుడు కొత్తగా మార్కెట్లో నానో యూరియా అని వస్తున్నాం సార్.
కరెక్ట్.
అది మనం 3 బస్తాలు వేసే యూరియాకి ఒక ఎకరాకి ఒక చిన్న బాటిల్ వేస్తే సరిపోతుంది అంటారు. అవును సార్, వాట్ ఈస్ అది యూస్ఫుల్లా కాదా? మధ్యలో యూరియా కొరత కూడా మన తెలంగాణలో ఎక్కువ వచ్చింది. దాని గురించి ఒకసారి చెప్పారా సార్?
సార్ ఓకే, గుడ్. సో ఇట్స్ ఎ గుడ్ క్వశ్చన్. నేను ఇంగ్లీష్లో ఆన్సర్ చెప్పొచ్చు కదా? కంప్లీట్గా అర్థమైంది, మొత్తం అర్థమైంది తెలుగులో. సో see, the thing is, in whatever fertilizers and pesticides, whatever we apply to a crop, we apply them plenty, including the medicines that we take. Always we do everything in excess because a lot of it is lost, right? Urea apply చేసిన తర్వాత it is lost, right? By next washing it is gone. So we need to prevent those losses, and that is why these are what are called either encapsulated nanoparticles or whatever it is. So they can preserve inside whatever that nano carrier and is given to the plant or whatever it is in a sustainable manner over a long period of time. When it is a nano form, it might stick to the root or a leaf or whatever it is for a longer time, and it doesn't get washed away, and it slowly releases urea, right? And it has been proven like a concept that it works, and then indeed nano urea is now available. But how many field trials have been done? Those things I am not very sure. But it is a very beautiful concept. I think we should all try to kind of use that and see, unless it is tried by many people and then seen in the field whether it is working or not, then it will happen. But this is the concept. You encapsulate into a smaller nano size particles, and it is sustainedly released wherever it is, like drug delivery, right? It is released to the location where it is needed, not everywhere. That's how you can reduce the dosage.
Thank you, sir.
So, if there are no further questions, I would like to call Professor Mallareddy sir to felicitate our speaker, Professor B.L.V. Prasad. Now I would like to call Narhari Shastri sir to felicitate Professor Malla sir.
Okay. Okay. Narendra, you also. Narendra, come. Come. I was not able to resist myself for speaking a few words, not about you, about Michael Faraday, who was actually cleaning the streets of UK, getting 29 pounds a month. He left that and joined as a bookbinder for 17 pounds. Because he was able to read the books which come when it comes for binding. So that was the ability to read. Then his life is full of humiliations. He was identified by the great Sir Humphrey Davy. And the type of humiliation that Michael Faraday went through when he went as an assistant from UK to France through Davy are miserable, especially from his wife. But in 1924, when Faraday was elected for FRS, only Davy voted against him. Everybody elected. And he was the 2 times president of the Royal Society. In the entire history of Royal Society, he was the only one who said second time that he does not want to be the president. So, when our Professor Prasad said that read about Michael Faraday, you can read about. Like that, there are so many people. The type of things, Mary Curie, if you read, the type of humiliations that she had. When you go to Paris Museum, you can see the gown and the gloves that Curie has used, where still they are radioactive. With that, Madame Curie has only one person who got Nobel Prize both in physics and chemistry. And after getting 2 times Nobel Prize, she was denied FRS. Many years after that, she got FRS and she was humiliated, personally attacked, and things like that. Because I wanted that this has to be, we should realize that our Vijayakant bullet and then scientists not getting anything, or these are the things that we have to do it. And if some of you have time, all of you, Shabana Azmi, you know. Shabana Azmi also you don't know. We all know she's a. And do you know Subhash Mukhopadhyay? There is a movie called Ek Doctor Ki Mouth. In 1991, it was released based on this story of Subhash Mukhopadhyay. It's actually Subhash Mukhopadhyay discovered the test tube baby. That lady, that Kanak Durga, she's still alive. And he was humiliated and killed by India. Subhash Mukhopadhyay, his story is Ek Doctor Ki Mouth, which was done on a slightly different thing. Actual story is test tube baby. Now the current procedure of test tube baby is also being used by Subhash Mukhopadhyay's thing. but in the movie it is like a leprosy. Pankaj Kapoor and Shaban Azmi has acted. It's a fantastic movie. This is Jatra, this is festival, have fun, and you can also get excited about knowing about things. And let us give a very, very big round of applause to Prasad. Great and amazing.
Thank you, sir.
Thank you, sir, for your kind words. So we now arrive at the one of the most exciting segments of today's program, which is a nano quiz. You all must be waiting for that, I'm sure. So the quiz has been designed to test your understanding of various concepts, discoveries, and applications of nanoscience and nanotechnology. And we hope this session will not only competitive but also enjoyable and enriching for the everyone who are present here.
So, before we begin, let's briefly explain the format of the quiz. So, we will be having different teams, as you can see in the board. In the display, there are teams made from different colleges with students and colleges written over there. So you can look into it, sit according to it, and we will be fast. Do it fast, make it quick. Yeah.
Sitting arrangement should be first 9 teams should sit here.
So team 1,
1 to 9.
1 to 9, come here. Display team 1 first. Team 1.
It's
Team
already
1
there.
to 9. Yeah. So team 1 to 9, come to this row. Okay.
Please come 1 to 9 teams. First team here.
Please have
Second
a
team
seat
here.
here.
Come fast. Check the names and come here.
Yes, sir.
Yeah, you can go there. You are in the first team. Yeah,
That is
you come
the
here.
list.
Come fast. Second team here.
there is a green synthesis method that is they are expecting some deep focusing on anode. Anode it is made up of like cathode is made of NBP. So what is the process during charge? Sodium from the anode. As you can see in the diagram, it is anode and cathode. During discharging, anode to cathode, during charging and cathode. So this happens through electrolyte. Electrolyte is usually made of sodium salts or lithium salts. So the energy density which we are aiming to increase is mostly dependent on what anode you use. The energy density is mostly dependent on material, what material you use. So here we have a point sensor. Here as you can see the particle positive and negative case. And in between anode we have fabricator. This is the anode. Okay. So this is giving a current up to 1 ampere, which is comparable to lithium-ion batteries. So, any questions related to this? Like, so have you faced any problems related to batteries? Like it is discharging fast. So, so that is due to some dendrite problems. So, whenever a particular ion is getting combined, it forms an with current density. So this ruptures the electrolyte that turns into short circuit. So fire, it is flammable. So that problem we are trying to solve.
Nanoparticles are a sheet of chlorine. When light is incident on the nanoparticle, they will of course rise electrons. So this light will apply force on the electrons. And since it's in the form of an electromagnetic wave, this will make my electrons oscillate. If my oscillation is wavelength quickly, my wavelength of oscillation equals the wavelength of the incident light. That as we change the particle size, the values change. So this can be used for multiple applications like sensors, categories, targeted drug delivery, etc. So you guys
have you seen this real-time application we have, right?
Yeah, so like for catalysts we can use them in sense. Now we have nanoparticles.
Filters also have.
Yes.
Drinking water filters, no? Yes,
it is expected to have good absorption capacity because it is very fast increasing. So we can expect it to absorb and it is very good filters.
Thank you. In the back, please.
So here are materials
Here. This is an empty project.
We are presenting something which has
masks. Nice. Thank you.
The Windows lock, normal cards, mutations,
Can you explain this?
Yes. So actually, it's a liquid crystal. So what happens is that polymer is subject to IQ glass. So what is glass? Glass is transparent, right? So what happens is that when we apply a small voltage between two glass, so in between there is a polymer with liquid crystal. Liquid crystals have a properties of liquid and work crystal. So the main property of liquid crystal is that so when the voltage is applied, due to its property, it will align. So what's so it will align with the electric field as a function. Yes. So this you see, if we are applying it now, we are going to apply voltage. Right now it is not transparent. You cannot see the object clearly. You can see, but 60% you cannot see. When I apply voltage, now all the lights are going smoothly. Means scattering is less. So in this mode, the scattering is smooth because the liquid crystal are not aligned. So when I am giving voltage, it will align in the direction of the electric field and it will give it scattering and it will be clear. So the possible applications of is that we have this curtains, car windows and everything. So we can have a dynamic on or off kind of privacy kind of thing. We can not a permanent. So what we do, we put film or curtains. It's like a permanent. So electrically, dynamically we can adjust this privacy, and it is compatible with current technology.
Now it is a trend, right? It's
Yeah.
upcoming. I have seen in the
It's an it's an ongoing research actually.
even in the solids also there.
Yeah, it's
Like there.
does it conduct in this G direction? A, B, C. C direction does it conduct? Yes. Right. Okay. Why is that?
In one plane, all the atoms are connected. So free electrons are important.
Once again,
in this direction, they are layers. So there is no conductivity between top and good. That is the example. Foldable and flexible devices. It is completely insulated.
Now, what is piezoelectric, first of all? I will try to take that through the answer. What is piezoelectric? Means what? Yes, no. They have done something. You press mechanical physical change should not be, there should not be no inversions. That is one important property because electronegativity and right? So that is the most important property that materials should have this way. Now my question is, right? Where do you see piezoelectric will be? And you have to explain. And you name and sir, can you explain your hand? What is that you are wearing on the hand? What is that watch? Is it analog watch? Okay. Previously, analog watches used to have springs. What is there now? What is this watch called? This watch is have what? What is the phenomenon? Right? Here it is exactly opposite to what you are seeing here. Here mechanical energy is converted to electrical energy. There you are putting a battery. Your quartz watch does not work without a battery. Right? Why do you need a battery? You put a battery, you apply small voltage, the quartz crystal vibrates. Here electrical energy is converted to mechanical energy. And when you apply a certain voltage, the frequency with which the quartz vibrates is constant. Its number is there, right? That is converted to time. Seconds and right? Okay. So there is no battery. Okay. You have to change the battery for quartz. This way many of these watches say quartz. Have you ever wondered why the watch says quartz? Right?
Not all colors, 3 of them. Can you tell? Up to IR range we are getting outside, up to 2000 nanometer. So there we can expect more efficiency. Here we can see only 30 microvolts or something. But for real use, that is not enough. We need more. At least it should be for small light also. In functions, we can see the small LED light that requires 1.2 to 1.5 volts per. So just image for our daily use, like how much we need. So we have to improve its efficiency. By that way, we have to.
Thank you.
Thank you.
Because you are, but any you may not work.
We are also doing
For commercial. Test for exhibition like this, test for
I'm dipping it in the silver nitrate solution. So over time, you can see that one black layer of silver is being formed on the copper.
Can I move inside, sir, once? Go ahead, go ahead.
What is the what will be copper?
What is getting oxidized, what is getting reduced? Okay.
According to the standard. No, we are talking about copper and silver. Yeah, metals. This is the reaction between metals.
Where do you see this? In daily life. I always think it's daily life. Because we stop observing it. Where do you see? I tell you, like, if I give the answer, you will all. I know this.
Copper utensils.
If anybody is observe moisture from the atmosphere, compared to last okay. So we are using some nanomaterials. We are using some nanomaterials which is sensitive to water molecules, which can absorb from the atmosphere. And because of this nanoparticles property, it can change the resistance. If the water molecules the number of flow of electrons, so if the resistance will be less. If it is dry, so accordingly you have to calibrate the system. These are actual units which will be mounted to below this mix, and these provide the flush for lifting. This one of the broad vibration and the other vibration. This was the actual project we had. Like
These projects we have made about 6-7 months back.
so during the pandemic we got. But it is going at a very speed. It's very low. No, sir. These 4 motors will only use for going to a certain level, and it will stop won't cause any problem during the flight because as they will be turned off, after which can ultimately no significant portion of the we can just do like that. And ground motion for going front and for going right, and again we use this focus for going.
Inspiring lectures, interactive demonstrations, and enthusiastic participation by every colleges that are present here. So today's event has truly celebrated the spirit of nanoscience and technology. So we sincerely hope that the experiments and interaction throughout the day have sparked curiosity and inspired many, in fact, all the young minds present over here to pursue science and innovation, obviously.
So, before commencing the valedictory event, I would like to invite someone from audience if they want to share any honest feedback. Few people have agreed on that. So, Madhuri from CBIT College. You can come here, Madhuri. Hmm.
Good evening, everybody. I am Madhuri from CBIT Hyderabad. We came for this conference. I would like to thank all the faculty, whoever is present here, Suresh sir, all the respectable persons here. We got a lot of exposure. Firstly, whatever projects that we have built, we are Team Astra from CBIT. We build rockets, satellites, and drones, and we are currently developing whatever projects we have, and looking. Is it okay? Yeah. Currently entering into nanotechnology, looking what we're currently using graphene sheets, how we can use them in our projects and improvise them. We got a lot of exposure. We got a lot of exposure here, honestly. Met amazing people, amazing faculty here, providing us so much knowledge. And it's an honor to be here, honestly. Let's have an applause for this conference. Thank you, sir, for so many useful insights for us. I hope our whole team will come here again and do a lot of fun stuff here. As in the morning, sir said, have fun. We indeed had so much fun. Thank you, sir.
So next, I would like to invite Shubham Datta from Dr. APJ Abdul Kalam College.
Good evening to all the dear sirs right here, and good evening to the faculty members right here. And thank you for ma'am to give me a chance to come right here. As a BSc Life Science student, I wanted to join like this innovations because my father every time took me to like this innovations. I have seen many exhibitions, and it is a chance for me to come here and stand and tell my remarks today. I like the lectures given by all the teachers right here. It is a nice thing that I had learned something from this nanoscience because I had interest in science from small age, and it was very nice to listen everything like videos, and it was very fun to be right here participating in everything. And that's all. Thank you.
So next, on the same note, I would like to invite Hari Krishna from Dr. APJ Abdul Kalam College.
Hello, good evening everyone, respected sirs and students. I am from Dr. APJ Abdul Kalam College, myself Har Krishna. In morning section, I learned lot about nanoscience and things. Murthy sir, Director Murthy sir said. In next section, Prasad sir said lot of things and enjoy very much in sir's class and learn many things. In exhibition also, there are many experiments are told and we learn lot of things. I am from BSc Computer Science Department, but I learned lot of things about chemistry, nano, technology, and lot of things. I getting interesting very much when I here coming and through IIT I learned lot of things. So I think special thanks to all of you. But I'm a computer science department, but uh, having much interesting in nanotechnology and chemistry. So thank you so much for giving lots of information and telling about technology. Thank you, sir.
So may I now request Professor BLB Prasad, Professor Nahari Sastri sir, Professor Mallareddy sir, and Professor Bhavani Shankar Malik sir, and Dr. Narendra Kura sir to come on dais and to felicitate the winners.
Yeah, they have given the responsibility of announcing the results. First of all, to everyone who have participated in this competition, congratulations to you all. I think this win-lose is a very wrong term to use. Participation is the most important here. And I think since morning, whatever we have been doing, it's not that daily we do these kinds of Bharatanatyam, Kuchipudi dances, right? Okay, this is when we come here because we want to convey the fun that we have had. Of course, behind that there are a lot of failures. There is a lot of there are a lot of challenges, and despite that, once you get a great result, that basically wipes off every other obstacle or the sadness that we faced previously. So I hope you have had a glimpse of what fun science can bring to life, and hope some of you, as I said, could pursue career in science, and many of you or all of you would take scientific temperament back home and then practice science in everywhere where you are, right? So that is extremely important, and if we have at least given you some kind of a thought or put a thought in your mind, I think we have been successful. With that, let me announce, I think this is basically the first, second, third positions, right? Okay, and let me go back from the third position onwards. Okay, taking the third, and let me tell you, the gaps were extremely small. In fact, we had to go back to the question answer sheets once again and then look them with a magnifying glass, and then of course we did not take anything, but we could see that we have very, very tight competition here, and congratulations once again to all of you. And the third position goes to team 8, Dheeraj, Husna, Fardoz, Sakali, Amika, Amisha, Laluri, Nishin or Shivani. Where are they, please? Please come forward.
Team 8.
Team 8, please. All the 5 are here, or some of them have disappeared? Only 2. Your teammates are not there? No? You did not take their numbers? No. You wanted to have all the money to you? Right? I think if that is the case, Narendra, I think you need to hold some money back and then distribute it to the other members as well. But nonetheless, thank you for being here, and let me give you the certificate or whatever. What is that being given? Envelope there. Okay. But I think Narendra, you have to take care of that.
And a common certificate.
Okay,
right
sure.
now.
Wonderful. Yeah. Come, please. Hey, all of you. Come here, come here. Big round of applause. And then give it back in proper proportions. I don't know. Take it. Yeah, sure. They know, otherwise those people will come back to you and then say that where is my cash? I know, that's why, exactly. Yeah, yeah. So you will get the money.
Oh, yes.
Okay. And taking the second prize is Team 6, Shakira Banu, Pranay, Sai, Mukshai, Nikita. All the 5 are there? I know, exactly. And they don't trust their 3 members. Come, please.
Certificate and envelope.
Please come forward.
Come. You don't want? Take care of the envelope and run away. Yeah, now you hold all of it. Lay hands on this. And now the moment we are all waiting for, right? Okay. Taking the first prize. He already wants to see it. Okay. Taking the first prize away. The winners of today's quiz are Team 9. Nandita, Shivai, Srimani, Chandrasekhar, Sai Srinivas. Okay. Again, all 5 are there. Yes, all 5 are there. And hope your team spirit continues. Yes, sir. Huh? You'll make it. Come, come, come. I know. Thank you. Thank you, sir. It's nice meeting you, sir. Congratulations, guys. Thank you. So yeah, I think after the whatever the formal conclusion happens, I will have one word. Okay, sure.
Sure, sir. Congratulations to all the winners for their outstanding performance. We also congratulate every participant for their enthusiastic involvement and commendable display of scientific curiosity and teamwork.
On behalf of the organizing committee, IIT Hyderabad and SENS, we extend our heartfelt gratitude to the distinguished speakers, respected dignitaries, faculty members, student volunteers, organizing committee, and every participant who contributed in making Nano Jatha event 2026 a grand success. Thank you all. So further, I would like to call on the stage Dr. Narendra Kurra for the closing remarks and vote of thanks. So.
Anyway, it's my pleasant duty to propose vote of thanks. So I'm sure all of you had a fun day today because of this Nano Jatha event. First and foremost, I'd like to express sincere gratitude to our Honorable Director Sir, Professor B.S. Murthy, and also the National Coordinator of Nano Jatha event, Professor B.L.V. Prasad Sir, for their delightful lectures and keeping the students highly engaged and giving importance of nanoscience and nanotechnology and then its emergence and very easy way of demonstrating things. We have already witnessed it. And after that, we had a very nice quiz that all of you are enjoyed the quiz, writing an exam on Sunday. That's always, and thanks to all of you for your patience and students coming from all the colleges and all teachers on Sunday, bringing them here and keeping the energy all the time. Truly, acknowledge. And then last, I want to acknowledge all the student volunteers led by Monit and Shwetank, Suman and Somaranjan. And then many more volunteers, the 16 of them are there, who actually helped with the exhibitions and also demonstrating to different batches, and their effort is highly acknowledged. I also thank PRO team led by Vinayji, and lot of effort they have put in doing the live streaming of this particular event so that it will reach to the wider audience. And also many more, because yesterday was a convocation event, and a lot of logistic issues have been taken care with the help from the supporting staff here, attenders and housekeeping staff, and every one of you, I thank you very much. And here we have technician AV Prakash, who kind of helped it in a very great way. Thank you once again, everyone. Thank you. Have a nice evening. I have one word to say. Then I take the national coordinator prerogative, right? Okay. Let us give a big round of applause to Narendra and the entire faculty of IITH
the volunteers.
Exactly. Yeah. That's what I wanted to do. Can I have all the volunteers come here on the stage, please? All the volunteers with the sky blue shirts. Call everyone, right? Quickly come. I also want to, it's my duty also to thank the government of Karnataka, Case Steps, which has actually funded this program because it's a very interesting thing, right? A state government funding the program and saying that you go wherever you want and then do this Nano Jatha. Come on stage, please. You are the main pillars for this. They deserve a continuous applause until all they take the stage. Continuous. Absolutely phenomenal team. Thank you very much. And I also thank my own colleagues who have Dr. Subhash and many other, Dr. Krishna Prasad and many others who have helped in making the kit like this and then helping us going everywhere. Thank you very much, and we'll have one group photograph with these wonderful volunteers. You can be behind. You will get a lot of reflection.
So, to mark the formal conclusion of today's program, we request everyone present to kindly stand for national anthem.
जनगणमन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड उत्कल गंगा विंध्य हिमाचल यमुना गंगा उच्चल जलधि तरंगा तव शुभ नामे जागे तव शुभ आशीष मांगे गाहे तव जय गाथा जन गण मंगल दायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे
So participation certificates are there in the registration counter. So we kind of segregated into colleges. So please collect.